Okay, I guess we can get started, although more people should join. But anyway, we'll get started. Let's not wait further. Okay, so very good morning, all of you. I hope you're doing well. Um, so today we are at week 2 of this module on deep learning. In particular, today we will discuss majority of the lecture will be on specializing the multi-layer perceptron that we discussed in the previous class, but fine-tuned to vision applications. So whenever we have images or any structured data. So far, the assumption was we have tabular data and there are features available with us, many examples, and there is no particular structure in the feature set. Okay, so that is the assumption that we were working so far. Now, today, what we will do is, suppose there is some structure in the feature. So we had this MNIST image example of a digit, and if we vectorize that, it was a 28 by 28 pixel, we vectorize it, we get 784 features, and particularly we did not exploit any relationship between the features. Now, if there is any relationship between the feature, now can we specialize multi-layer perceptrons to reduce the number of parameters, right? So that basically leads to what is known as convolution neural networks. Predominantly, this is used for image-based tasks, but we will see as we progress that we can also use this for time series with certain limitations. Okay, that is what we will focus on today. So the roadmap for today is the following. We'll do like a one slide a summary of what was discussed in the last lecture. I mentioned there was two things that I will go through again, the MLP for classifier and regression problems. And then, as I mentioned, most of the hyperparameter tuning was left as a reading material that was so towards the end of the slides. But today I will focus on two very important and highlight some of the aspects that require some specific care. So I will go through that. This is this is kind of engineering tweaks, but essential to make sure that the network that you're training works well. So the rest of the class will be focused on what is the main topic for discussion, today's discussion, that is CNNs. We will break down CNN into multiple smaller blocks. For example, you see things like convolution, padding, striding, and then we will discuss one basic architecture today. And again, you play around with that during the week. Next week, beginning, I will focus on one advanced architecture. Okay, so, but you will readily see that different architectures that are out there, ResNet, ImageNet, etc., are mix and match of these basic building blocks. Some of them will have like 3 layers, some of them will have 4 layers, etc. Right. So that is what the changes are, and you will you will see as we progress what are these differences. So that's the plan for today. I hope you all can see my screen and the audio is clear, right? There are no issues with the audio.
It's clear, sir.
Very well. Okay, so let's get started without further delay. So recall, this is a summary in one slide. So I usually give one slide summary in the beginning to quickly recap and build upon the content that we saw, so that it is also a bit more fresh compared to what we had seen, and also gives you that main take home message. So that is the pattern that I will follow for rest of the weeks as well. So recall, we were trying to mimic a neuron which basically triggers something after it receives sufficient inputs. Okay, now we wanted that to be adaptive. The way we made it adaptive is to combine features. Okay, so combine features. And now how should I combine features? We cannot hardcore it, but we let the training algorithm to decide how to design these weights and biases. Okay, so that is what we can play around whenever we are discussing any neural network models, right? So be it MLP, CNNs, RNNs. So there are some tunable parameters, and the way we use those weights is basically to combine features, and it is going to figure out what features are relevant. Okay, the features could be engineered features, but as we will see, it could be raw data without any particular engineering task as well. Now, that was the perceptron, and we saw that, okay, whenever we have a perceptron, you can basically play around with a line, right? So we basically have like y is equal to mx plus c type of equation with some nonlinearity. So you can play around with the slope and the offset. But oftentimes, as we will also see in today's earlier part of the discussion, that you might often require more labels, right? So multi-label classification or multiple binary class classification. So you require multiple outputs. So what we could do is we could put these perceptrons one next to the other, which basically means that compared to whatever we had, the W's and B's in a single perceptron, you're going to increase the number of parameters. Okay, so that means that you have more parameters to learn, which also means that you have more degrees of freedom to basically obtain something that's more useful than what you can basically do with combining with a single set of weights. But we also quickly realized that simply stacking uh, perceptron one next to the other horizontally has a limitation, with in the sense that you cannot obtain decision boundaries that are beyond linear. So if there are classes which are not linearly separable, then you require something more complicated. And with a hardwired set of weights, we saw that for a simple task like the XOR classification, if we do go from a single layer to a two-layer, and more generally multi-layer, we can basically uh, get more complicated decision boundaries. Each layer, each perceptron, as usual, has some nonlinearity. It is basically a linear transformation plus nonlinearity. And you do that many times. That is what brings a multi-layer perceptron. What we also realize is that during this process, we do something known as back propagation. We don't have to explicitly compute the derivatives, but this is automatically computed using something known as automatic differentiation. And that happens behind the screen. We don't even see what is the gradient. We don't even care about what the gradients are unless we run into a problem, right? So if we see that the network is not training properly, then you require some kind of inspection about what is going on with the gradients. But with that simple calculation of back propagation, which basically involves splitting the data into mini batches, because we don't want to dump everything into the GPU, whatever data we have, we will split that because GPU size is kind of fixed. So we need to reserve memory for loading data, storing all these weights and biases that we do. And we also saw that not just the weights and biases, but in order to simply compute this gradients, we also require to store some miscellaneous vectors and matrices. So basically, we require memory for that. Now, given that there is limited memory, what makes sense is to work with small chunks of data and go through all the data in small chunks, right? So that's basically stochastic gradient descent. So we do that for many iterations. Okay, so that is the training process. We will see with an example as we go further today. So, but the main thing is doing that computation. What we saw is that we require to compute the gradient of the activation function. Now, what that means is whenever we are computing the gradient of an activation function, like what we see here, you require the gradient to be something more interesting. For example, if you see this activation function, which was a step function, right? And if you look at the gradient, most of the places, wherever the gradient you can compute except for the zero, which is not differentiable, most of the cases, there is no change happening, right? So the slope is zero. There's no slope means that it should be a ramp, right? So there's no slope. The slope is zero. Nothing is changing. So the derivative is basically zero. Now, what that means for our method is whatever you're computing here, if this becomes zero, then you're computing an update as wk plus 1 is some wk minus eta times the gradient of this function, right? So this is the expression for the gradient. Now, okay, whatever method you use, right? So forward, backward differentiation, back propagation, if this comes to zero, then there is no movement happening in terms of the update. You start with some initialization W0, you are stuck basically at that point because whatever gradient you're computing, it is being multiplied with the gradient of this activation function. Now, that activation function doesn't have any gradient, which means that you're not updating anything, right? So that is what we need to keep in mind. This can happen not simply by choosing any arbitrary activation functions, but it can happen for several other reasons which we will discuss as we progress maybe in the next lecture as well with the issue called as vanishing and exploding gradients. So for this purpose, the step function in the original perceptron model is often not used in practice, but people use smooth approximations of the activation function, which is, for example, a sigmoid function. If you look at the sigmoid function, the majority of the region, right? So between -1 and -2 and +2, or in fact -1 and 1, this has a slope that is non-zero. Okay, so there is some change happening. And the other common activation function is the so-called Rayleigh activation function, which is basically giving only positive outputs whenever you have positive. So here also the gradient is non-zero. The other smooth approximation of the activation function is the tan hyperbolic activation function, which is basically stretched version of sigmoid. Instead of going from 0 to 1, you have from -1 to +1. So these are all smooth approximations that basically enable training of the neural network. Okay, so these are the things that we need to keep in mind from what we have seen in the previous lecture and take this is the main take home message. Okay. So now I'll go through a bit about the activation function. So I already mentioned that we require this to be non-zero. And for that reason, there are more practical activation functions. There are basically a list of about 15-20 activation functions, but I'll go through two of them slightly more in detail. And when do we use this? Some of this you have already seen, for example, in logistic regression, right? So logistic regression, and hence it's called as a logistic function or a sigmoid function. So we have some kind of a smooth approximation. So before we had something like this, but now you have a smooth approximation function. And if you look at the gradient, and mostly the interesting region is between -1 and 1, I will tell why this is. So you see that the gradient is non-zero. Now, when would you use this? Suppose you are looking at a classification problem, a binary classification problem, then you want this outputs between 0 and 1, where the outputs are interpretations of the probability of the likeliness of a class, right? So with what probability that class is true, right? So that's giving you a class probability. So the probabilities are between 0 and 1. 1 being very likely, 0 being not very likely. So in that case, you would use a logistic function. And similarly, like, okay, if you train this, or even with this hardwired XOR classification problem, if you look at the decision boundary, where recall that while doing this XOR classification, we somehow hard computed the values of the weights, right? All the grays are weights 1, and then the red ones have weights indicated above it. You see, this is the decision boundary. But with those set of weights, if I replace the perceptron that had a step function with a sigmoid function, then you see that the decision region is very similar. It's not, it's basically a soft thresholding, but gives you a region that is still useful for classification, but not very crystal clear like the step function. So there is some approximation. So you're not getting 0 or 1, but you get values between 0 and 1. But that is what is required to let the network train. Okay. Okay, so now let's look at a couple of more activation functions. So the other one is a tan hyperbolic activation function, which is again, like as I said, it's an expanded version of the sigmoid function. But again, the reason for using this is like, okay, beyond classification, for regression, suppose you're looking at putting a bounding box around an image, and now we know that the bounding box should be within this region, so within -1 and +1, with some scale that we can artificially learn that is going to expand the size, right? So you require that the outputs are bounded, then you use tan hyperbolic. Again, you see that, okay, the most of the regions of interest, 1 and -1, it has a non-zero gradient. Similarly, whenever we require positive outputs, right? For example, you're looking at house price prediction. So house price is positive, right? So it's not negative. Then you can use this rectified linear unit ReLU function, which is again having a non-zero gradient of 1 in the region of interest. Okay. So now the design choices, when to choose which one, we'll see that the output layer and the input layer is basically not under our control. It is determined by the problem at hand. Whereas the intermediate layers, you have flexibility to play around. You can choose tan hyperbolic, ReLU, sigmoid, etc. But oftentimes the choice is basically ReLU because it is very simple. You don't have to do any particular computation. Like you don't have to compute this exponent and do a lot of computation. You just look at the value and then select one, right? So that is often the design choice. Now, if that doesn't work, then you use something more complicated, okay? So now what we will do is in the next 5 to 10 minutes, I'll take you through how to program the MLP classifier for classification and regression with a pedagogical example. And you will see during the process, as I said, like the output and the input is basically determined by the task at hand, which is classification or regression. The input, you have some leeway to play around, and some design choices by experience is what we will see. ReLU is for hidden layers. ReLU is the default choice. So you would choose one version of one of ReLU. Also has many variants, right? ELU, SELU, etc. So the default choice is to start with ReLU for all the hidden layers. And experiments and experience says it works 95% of the time without any issues. Now, if you want to see if ReLU doesn't work, then you start looking at, say, a variant of ReLU or so on. The math expression for ReLU is simply this, right? So if at all Z is the input, then you take between whichever is max. So if basically it doesn't do anything whenever the input is positive. So this is a linear line with slope 45 degrees. So for example, ReLU of 3 is 3, ReLU of minus 3 is 0, right? So whenever it is negative, it basically gives 0. ReLU of minus x is always 0. ReLU of x is x. That is what it is. Tan hyperbolic, name indicates it's tan hyperbolic. Logistic is the logistic loss. Okay. So now classification, what is the classification problem? You have many training examples. Each of them belong to either positive class or negative class, or it can belong to many classes, out of which always one is true. So this is an example of a so-called fashion MNIST, where each image here is cleaned up. No natural image appears like this. All the background is removed, etc. This is for educational pedagogical purpose, where each image is 28 by 28 pixel. What we do is we vectorize this, reshape it as 784 times 1. These are grayscale images, pixel intensities between 0 to 255. Okay, now we have 10 classes here. Our goal is to classify, learn a model such that when I put one of this image as the test data, it should output quote, which or something that resembles quote in terms of the encoding. Okay, so how do we do this? That's the task that we will see. Now, in classification, you might have already seen this in the previous modules on ML. Classification, you have three types. One is binary classification problem, that is a 0 or a 1 output. So you get 0 or 1. Multi-label classification, so you have many 0, 1 outputs, right? So this is like you have 0, 1, 0, 1, etc. Each output is independent of the other. For example, if you want to classify email as the following, right? So it is spam or ham, that I can decide with one variable, urgent or not urgent with another variable, each of them being 0 or 1. So I require two outputs. Binary classification, you only require one output, that being 0 or 1. Multi-class classification, again, you might have seen this, like also what we saw in the previous class. There are digits, 10 digits. At any point of time, you can only have one digit as an output, right? So that means that the classes are kind of exclusive. So you cannot basically have two classes at the same time. So in all these classes, in all these problems, what you see is that whenever I want to design the output layer of a neural MLP, then the output is determined by which task am I focusing on. If I'm looking at a binary classification, then I'll have only one output. If I'm doing multi-label classification, then I'll have as many outputs as the number of labels. If I'm looking at multi-class classification, again, I'll have as many outputs as the number of classes, but the activation function is again determined by the type of the task. So for example, if I'm looking at a binary classification problem, the output I would use as a logistic activation function. The output layer has a logistic activation function. And if I'm using a multi-label binary classification, again, for each of the outputs, I'm using a multi-label classification. Multi-class classification, the output activation function is a softmax. What does softmax mean? Recall, multi-class classification, again, an example is this fashion MNIST or this handwritten MNIST digits where you have 10 digits. Okay. Now, if I have, say, 10 digits, I'll have like what we saw before, I have 10 outputs. And what does softmax do? Softmax basically outputs a score between 0 or 1, such that if I add all the scores, it should sum to 1. Because it's an interpretation of probability, it should sum to 1. The total probability should sum to 1. And each output is telling which class is likely with what probability. That is softmax. So handwritten digits is an example of a multi-class classification. Fashion MNIST is an example of a multi-class classification. Again, I have 10 classes. So 10 classes of whatever apparels, right? Sneaker, boots, t-shirt, dress, etc. Right? So these are 10 classes. One of them will be active, but since we are using a softmax, we will see that, for example, if you're looking at say a model that is trained. Now, if the test time or the training time doesn't matter, if the input is a t-shirt, then it could give a score of say 0.7 for a t-shirt, and t-shirt or top, it could be yeah, I mean, so something else, right? So let's look at a dress, right? So it looks very similar. So this could be say 0.2. So it is giving you some confidence value that, okay, very likely it's a t-shirt, but it could be with small probability a dress as well, right? So that is what softmax does. But now it could again be something else, like a shirt with a probability 0.1. So when you sum all this, it should sum to 1. So that is multi-class classification. Okay. Now, these are the 3 tasks typically in classification. Now, I know which task I'm dealing with. As a consequence, I know what is the output activation function I need to choose. Now, what remains is how to choose the loss function. Okay, so whenever we are using a binary classification problem, the first task or even the second task, what you would use as a loss function is what we have been usually using. It is the binary cross entropy. And this binary cross entropy, what we will see here is the following. So you have labels with you for the ground truth labels for the training data. The loss function is basically similar, exactly same as the loss function that you use for logistic regression. But what is changing now? The change is that it is not a linear function with some logistic loss, but I have, for my hypothesis, with a multi-layer perceptron, I have the following, right? So I have sigma, which is a nonlinearity, applied on, say, my feature, which is xw. So we had xw plus b, and then again, this is a new feature. So I'll have I'll rewrite it somewhere here. That is not responding for some reason. So we had xw plus b plus nonlinearity, and then you have one more nonlinearity, which is xw plus p. So this is like a 2-layer MLP where you are learning W's and P's, but now this is our hypothesis for the prediction, right? So the label prediction, this is our hypothesis. You're not simply using the logistic like what we had for logistic regression, but you use the multi-layer perceptron. Now you use that in the cross entropy loss function. So we know what is the output layer. We know what is the loss function that you need to pick. Okay. So similarly, if you're using a multi-class classification problem, the hypothesis will always remain the same. What changes is the loss function. The loss function will also determine what W and B you're learning, because you're always optimizing the loss function. What that also means is the W's and the B's that you learn for a multi-class classification will be different from the ones that you learn for a binary classification. Okay. So now putting all these things together, we can summarize how to cook up an MLP for classification. Recall always, the input and the output is not under our control. All we can play around is with the hidden layers. Input is determined by the number of features. If the input data, in our case, we are doing something on MNIST data sets, 28 by 28, number of features are 784, vectorizing 28 by 28, 784. That means that the number of input neurons or the number of neurons in the input layer is 784. Okay, so that is what will be the input layer, nothing under our control. The output layer, MNIST, I'm doing multi-class classification, 10 classes, I already know. So 10 outputs. It is multi-class classification. The output should use a softmax layer. That is also known. What changes? How many input layers should how many hidden layers should I use? How many neurons should I use in the hidden layers? So those are all the hyperparameters. So the number of hidden layers, number of neurons per hidden layer, activation function, the optimizer, like you want to use Adam, simple SGD, etc. What is the learning rate of these optimizers? So all these things are something that you can play around with. Now, there are certain towards the next 3-4 slides, I'll show what is a typical number that you need to choose. But if you say, okay, I'm getting say 93%, and I would like to see if 96% is possible, then what you need to play around is with this. Okay. So output layer activation function, logistic, softmax, cross entropy is the loss function. How do you optimize? It is up to us to choose. Okay. So now what we will do is we will go through this particular example coding, and then so the activation function itself, there is a list, right? So we saw ReLU, tan hyperbolic, etc., right? For the hidden layers that you can maybe play around. Okay, I use ReLU, I get 95%, and I use say logistic also in the intermediate layers, then I get maybe 95.5%, right? So that freedom is still available with you. So let's go through this step by step. That will answer some of the practical questions that I see one of you is asking. And then I'll again just flash the same for the regression task, and then we will move further. Okay. So now fashion MNIST, 10 classes. What do? You load the data set, right? So I'm using Keras. PyTorch is again the simple logical construct. It's with PyTorch, Keras, or whatever is available out there. Some of the data sets are already nicely available. Some of them you have to crawl, but the point is you divide the data set into train and test. You never use test for training the network. Training data set will have two parts: features, labels. Features in this case is 784 times whatever number of examples you have, and the labels are for each of this example, you will get a label which is coat or t-shirt, one of these. Now, often this is a class name, right? So related to the question that Jayanti is asking, the label will be as a one hot encoding of this. So for example, if the first image is the training example, the code, so then it will have a non-zero entry of 1 here and 0 everywhere. So that is basically a one hot encoding. That is the class label. So basically you will have for each image, you will have a 10 times 1 vector as a label vector. Okay, so that is what we will have as label. Okay, so what output we get for the prediction, that will not, ideally we want it to be a one hot encoding, but what we get is a softmax score. Okay, which means that it can be between 0 or 1 each entry, but when you sum all that, it should be summing to 1. Now, we have 28 by 28, so you do reshaping, and for this particular example, there are about 60,000 images, all cleaned up. In practice, you will never see such a beautiful cleaned up data, but for understanding, this is what is needed. So we have 60,000 examples in the training. Now, what is very, very, very important is whenever you have data, you always do something known as a standardization, which means you're scaling the image so that it is between 0 and 1. I'll come back to this again later, but for now, because these images are grayscale 0 to 255, you simply divide by 255 so that you reduce the dynamic range so that it's between 0 and 1. Okay, so that's pre-processing of data. Now, the model building is very simple. What you do is simply write this in English as you see. You do flattening, becomes 28 squared, that is 784. You have a 2-layer network, 2 hidden layers, 1 output layer. The first hidden layer has 300 neurons. The second one has 100. Hidden layers, you specify what is the activation function, in this case, ReLU. The output layer, softmax. We require 10 outputs. So this is kind of determined, this is kind of determined. So this 300, you can use 400. This 100, you can make it 200 or 10. See what the outcome is, right? So there's no general answer that if you make 300 to 600, you would get more accuracy or less accuracy. That is up to you to choose. Okay, so that's a hyperparameter. I'll give, there is no intuition, there is a suggestive list, but there is a way to fine tune that. We will see what that is. So now, recall in the previous lecture, we did a hand computation of how many parameters you will be training, but you don't have to actually do that. But there is something known as model summary. So what model summary does is basically gives you what is the total number of parameters that you're dealing with. So in this particular case, the first layer doesn't have any parameters to train. Those are the inputs. The second layer, it basically has 300 neurons. Recall how many arrows would go from 784 to 300 plus 300 bias. So this is the size of the weight matrix at layer 1, and this is the size of the bias vector. And this you can do comes to this number. Okay. Now the second layer, again, this is kind of easy to see. The second layer would have 300 to 100 plus 100. So it's easier for you to believe me in this case. So this should come to this number. So now you add all this. This is the total number of parameters that you would train. Okay. So all the parameters here are trainable. This is a cooked up example, right? So this might be an overkill. You might not require these many parameters. Perhaps doing this might not give you a significant improvement from the softmax regression that you might have seen in the previous module using whatever algorithm that you were using. But this is to give you an illustration, right? So this is not that, okay, you have to use 300 neurons, right? So there are better architectures, there are better numbers that you can play around with. But just if you use 300, this is what you would be dealing with. And clearly, if the technology was not advanced and you were to compute the gradients for these many parameters, very likely AI and neural networks would have not been very popular, right? So, so the most of the credit basically goes to the automatic differentiation tool that was developed, right? So that's very instrumental if you see what is required or what enables any one to basically train this, right? So now, if this is what is required, you would also at the same time appreciate why you don't need to understand whatever we did so far to basically code this, right? So anybody who has a vague understanding of what is going on basically can ignore all the math behind it, etc. Simply use this as a tool, right? So without, if it's the goal is not to develop new tools, to understand why is it working, why is it not working, or what should I make it to work. If I just want to use it as it is, anybody can do this, right? So a basic knowledge of Python programming and a Gmail ID should basically help you to code this and try it out. And that is one of the reasons why it is more accessible and also becoming popular, right? Of course, that is, yeah, just knowing that is very limited. But what we're trying to also see is like what happens behind the screens. So you do a model summary, you get a fair idea of what is going on, right? You're not yet compiled anything, right? So this is not a training. Now, when you want to compile the model, you will have to specify what is the loss function. So this is basically the cross entropy loss function, but the cross entropy loss function with this categorical one hot encoded vector being the label. So that is what you would do. You would pick what is the optimizer, SGD. SGD is what is required basically to solve that optimization problem, right? So you need to specify how do you want to solve that gradient descent, whether you would like to use whatever equation that I gave, right? So k plus 1 is equal to wk minus eta something. That is stochastic gradient descent. Now, there are other variants like Adam, etc., which we are not going into the details. So those are variants of SGD with some more additional features to basically make convergence faster, etc. Right? So these are variants around SGD. Okay, so to basically better accelerate, etc. So you could basically pick what is the optimizer from this list. Okay, so there are like about 15 odd optimizers. You also already saw that in one of the poll questions before. So that is what you would pick. Now you do compilation, and then once you run the model, this is kind of what you are getting at the output. You see that as training progresses, the accuracy increases. Now there is something called as a validation set. So I maybe I'll quickly mention what that is. So you have this training data. Training data, you typically in the setting that we work usually to test the model before deployment, you use the entire data set available as training and test. You split this into training and test. Now, within this training set, you would do a further split, which is called as again train and validation. Okay. So now the training data is what you actually use in the training. Validation data, what you would do is you would use that for hyperparameter tuning. Okay, so I train a model. Now I would like to test that model. And for testing, I use the validation. Now I use the validation score to again say change the activation function, change the number of neurons. Okay, so you still use a part of that for training your network, but you might not necessarily use the labels there. The labels could be used for plotting the accuracy, right? And you say that, okay, accuracies now could be better. So now let me fine tune the hyperparameter. So validation is part of training. So, but used for hyperparameter tuning. Testing data, you never use that. So once the model is frozen, test reporting the accuracy, etc., is done for using the test data set. Okay, so validation is used for hyperparameter tuning. So you get training loss, validation loss. Now, what is typically desired whenever you are training a network is that the training loss and the validation loss, or the training accuracy and the validation accuracy, follow each other. So for example, what is desired is the following. So I have an accuracy that I'm having with training. Okay, so after say 100 epochs, right? 100 is some example number. It reaches an accuracy of 95%. Now you are testing on validation data, plotting accuracy. So what you desire is that the validation accuracy also follows the uh, training accuracy. Okay, so this is validation and training. Now, whenever training, you're only using training to figure out all the W's and the B's. What is not desired is the following. So you have epoch. This is accuracy. Accuracy or loss function, depending on you're using regression or classification. So you could have, like, for example, in 30 epochs, you reach accuracy of 100%. But in validation, you see that you get accuracy of 30%. Okay, this is validation. This is not desired. What this is basically giving you is overfitting, which means that you are throwing away too many neurons, too many parameters to make sure that the accuracy is getting to 100%, but it is not generalizing to the data it has not seen. Okay, so it is doing everything to make sure that on training data, you get very good accuracy, but for data that it has not seen, it doesn't perform well. So what is desired is that the model generalizes well for data that is not seen as well. Okay, so that's something very important. The other important thing that you also need to keep in mind, this is again the part of tricks of trade that I mentioned. So you could, for example, while training, you would get say 95% at some epoch. Now you keep on training, and what could happen is that the accuracy might drop down. Okay, so now this could be, for example, 70%. Now, what that basically means is that you can potentially stop your model here and not use the model that you got after those many more epochs. But you should also see that the validation is also following this, right? So if that happens, such as thing criteria is called as early stopping. You need to stop your model early. Okay. Now, the other criteria that is often used to test the model, right? So this is again, see, the test that I mentioned here is before deployment. This is still like you are at the lab setting where you are figuring out if your model is worth to deploy and send it for production. So often the accuracy that you report or the loss function that you report is for one realization. Now, what is typically done is on this and this, you shuffle the data. Okay. So what that means is, so the example one was here and example, say 10,000. Okay. So 10,000 onwards becomes test data. Now you randomly shuffle. Okay. That shuffling would mean that, okay, so the 10,000 would come somewhere here and then example 3 would go here and so on. So these are creating multiple folds of the data. Why is that required? It is required, for example, to compute the standard deviation. Okay. You could use multiple initializations of weights. You could use multiple data folds. It is called as a k-fold validation. These are required to again choose, say, hyperparameters over the best set. If it is only hyperparameters, then you do a shuffling over the train and validation. But if you are looking for plotting, most cases you might have seen, right? So this is like plus minus 0.01. So these are the type of results that you might have seen. So this is required to essentially introduce some randomness in the data to see how sensitive is a model to the order of the training data, right? So it could be that, for example, in the data that is given to you, the first 10 examples are of digit 1, second 10 examples are of digit 2, and so on. It's like pretty deterministic order. And with that order, maybe you get like 95% accuracy. Now, the moment you do a random shuffle, it could be that the accuracy drops to 70%. So now you want your network to be robust, not to some particular ordering of the training data, right? So these are the typical ways to report accuracies, to train your model, and some of the cases where you need to avoid. Okay, so that's called k-fold validation, right? And multiple weight initializations again would give you robustness of the model to the initialization of the weights, but the shuffling would give you robustness. It gives you a better picture of how the order of the data is, how the weights are initialized, right? So this is a typical approach. So now when you do prediction, you have a softmax score, right? So for example, if you look at for three different examples, you see that, okay, this is 0.9, very highly likely, but it has also slightly less confidence in the model. And maybe it is saying with 2% chances, this class might also be true, right? So that is what softmax typically does. Okay. So now let's take this poll question just to reflect whatever we have. Let's see. Yeah. Understood. So now let me end this poll. So we are looking at a binary classification. The question is how many output neurons we require. I'm going to end this poll. So I see that many of you I've got this right. Majority, actually, most of you have got this right. So you require one output, and since it's a 0, 1, you use a logistic. Now, suppose I'm using a multi-class classification, I use a softmax, right? So that should be the point that you need to keep in mind. Okay, so now I'll quickly go through. The story remains more or less the same for regression. I already showed the snippet in the previous lecture, but what is worth mentioning is to recap what is regression and what changes in the model. So what you should appreciate now is the following, right? So MLP, the input all the way up to the output doesn't change if it is a regression or a classification, right? It is the same box. I can ask that box, fine-tune that box for behaving differently for a regression. Within regression, I can use the same box for behaving differently for uh, binary or multi-class classification. I can also use it for regression. So that's the abstraction that we should all be able to appreciate at this point. The training procedure is the same. The algorithm does not change. All I need to change is maybe the last line, what is a loss function, right? So with these three, yeah, this one you need not change. This one, yeah, I mean, it depends on what we want to see, right? So accuracy plus loss is what we can say. Loss function, the moment you change the loss function, the training procedure is the same, but the way the training is done changes, right? So it's kind of this generic purpose box that can be used for many things and fine-tuned for many things. That is what it should matter. So now for regression, what is regression? I have many instances. I would like to fit a model. And then there is a new instance that comes for which I need to predict what the value is, right? That is regression. So house price example, you might have like many features, right? It's not an image like classification anymore, but you have features. And then for each of this example, there will be a house price attached to it. Now, within regression, you would have typically two tasks. One is predict one value, for example, this house price, or you could predict multiple values. And for example, okay, there is this image. You do a lot of processing like what we will see good part of today. But the task is I would like to put this bounding box. Now, what that bounding box means is like I need to specify the center, the length of the dimensions of the boxes, etc., which basically means that it is a multivariate regression where you need to predict more than one output. Okay, so that basically what it is hinting is, depending on what are you predicting, is it a single value, is it a multi-value, then you will basically have a single output or a multiple output. Now, what changes? The hypothesis. The way we do hypothesis is not simply a linear model, but it is the multi-layer perceptron. The output of the multi-layer perceptron is our hypothesis for the value that we predict. Now we use a mean squared error loss function, or if there are outliers in data, you would like to be robust to outliers. So for example, if there is like an outlier somewhere, which is behaving differently from the nominal, you don't want a model to fit each and every point, right? So you would like a model to ignore a few points, but to fit what is nominally appearing. So then you would use a MAE, mean absolute error, or a Huber loss, like what you might have seen in the ML module. Now, whenever we are predicting, say, house price, you want a positive output. Nobody is gonna give you money and also give a house price, right? I mean, give you a house, right? So it cannot be negative. So house price is positive. For example, if you're predicting a stock change, right, a value change, then it can become negative. So it depends on what is a task we handle. If you want a positive output, you could use ReLU. If you're putting a bounding box, you know that the bounding box the is, for instance, like it could be 1/4 of an image, right? So you know what is the size of the image. So it be bounded between -1 and 1, and with some scale that you can adjust afterwards. So what changes? The output layer changes. How many outputs again changes depending on the task at hand. So this is again kind of a nutshell of what is required for a regression MLP. Number of input neurons determined by the task at hand. Hidden layers depends on the problem, but most of the problems you would go with, say, up to 5 hidden layers should be more than sufficient. Number of hidden neurons, I would go somewhere between 50 to 100. Depends on the task. Hidden layer, you use ReLU. Most of the time it works. If it doesn't, start with some variant of ReLU, again from that list, right? So uh, there are like at least like 6 variants of ReLU, one of them that you could start with. Output activation function depends on the task at hand. Bounded outputs or positive outputs, you would use ReLU or tan hyperbolic. Loss function, we already saw. So now the code, what would change? You can basically use the same model as before. Only thing that changes is the loss function. Okay, that's as simple as it can get, right? So now you are able to appreciate what is classic difference between the classifier and the regressor. So again, let's take one more poll to uh, for you to think, how would you design this network for the simple task, right? So now I'm not only interested in house price, but I will also want to see what is the rent income that I get if I buy that house. Okay, so I want to predict these two things. And there are some input features like, okay, how many bedrooms, area, neighborhood, how many bathrooms are there, and so on. So these are the attributes. So there is somebody who designs all these attributes. There's a feature engineering going on, but keep in mind, our goal is to do this feature engineering automatically, like what we will do next. Okay, I'll end this poll now. Okay, so I'm happy that about 90% of whoever answered this poll got the right answer. So the message is kind of clearly conveyed, right? That is, so we have 12 attributes. So you take 12 input neurons that is going to combine these 12 attributes. What happens in between? Not asked here, but you would choose based on the parameter selection. Output neurons, I require 2 values to be predicted, right? So price and rent, and that is determines the number of outputs. Output, you can use simply ReLU for both the outputs, right? For example, like, okay, you can, for instance, also put some common sense into the model. For example, like, okay, the house price cannot be infinity, right? So it can also be bounded. So you could choose a variant of that that restricts, that puts a cap on the house price, right? So if you have some knowledge, or if you can if you can put a bound on the upper and the lower bound on the rental income. So those all things can be, these are engineering choices, right? So depending on what suits for the problem. So in a nutshell, this is one slide that you can keep as a reference for as a design tool, right? So for MLP, for classification or regression. Okay. So now at this point, what I'll do is maybe if you have any questions, I'll let you guys unmute before we take up further. So
Professor, one question.
yes.
We use the activation function that is to progress or to converge, right? But why do we also need optimizer?
So the optimizer, so this equation that I told you, right? This WK plus 1 is equal to WK. So the update. So that is SGD.
Professor, that equation is common for all the optimizers or only for SGD?
No, that equation is for SGD.
For Adam and all, it will be some other different
Adam, it
equation.
will be slightly different. It will follow. See, I mean the basic logic that I have to update the current weight with something. Now, for example, like what you could use is I wanted to include these things. Maybe I will do this at the end of today's lecture if time permits. So see, I mean, new is current plus something. So what is common across all the optimizers that you see is this particular logic. You have to start with some iterative approach. Now for SGD, it uses something like this. Okay. So negative, go in the direction of the negative gradient with some step size. For Adam, this would be something like some matrix B times W, right? So, but what changes is this something between the methods. And that could mean that, okay, I'm choosing a smarter gradient, or I incorporate some other information. So that is going to give you, say, instead of slow convergence, it might give you a slightly faster convergence. There is something called as Nesterov method, Nesterov acceleration, or there is something called as Nesterov accelerated Adam. So these are all like variants. There are 10 different variants of all these optimization problems, but the main logic is this. And what changes is this something. Okay.
And also, Professor, one more clarification. So I didn't understand properly. How do we decide on how many hidden layers we need?
So there is so whatever numbers you're seeing here is right. So that is based on experience from a lot of experiments that people have tabulated. There is no formula to arrive at it, right? So this is based on historical evidence that, okay, for many of the problems, if you choose like say 20 hidden layers, it should work.
Okay.
Okay, so there is no formula to arrive at this number. So it is like you have this, it is like a Lego box, right? So
Okay.
now you have to basically put things together and say for one task that you are doing, okay, you might use 20 hidden layers. That works fine. And tomorrow you'll do something else. That doesn't mean that 20 layers or the same network might use, but okay, now you do something like 25 layers. That might be the best. Okay. So maybe I wanted to do this. What I'll do is maybe after we end this class today, I'll take 10 more minutes to go through this. This is kind of important, but we can skip it for now. Come back to this at the end of today's lecture, right? So like a 5-minute uh, uh, introduction and 5-minute extra I will take to cover this, which is what I plan to do, but let's skip that for now, but we'll come back to this at the end, right? Yes,
Yeah,
Rupesh.
Professor, I want to know what exactly the difference between multiple epochs are happening. Is it the data batches, like data chunks which we are processing, or weight initializations, or what exactly is the difference between multiple epochs
Okay,
happening
so
behind?
multiple epoch. Okay, so when you see a training versus epoch, right? So I guess this is what is your question. What is happening from 1 to 2 and so on, right?
Yeah, the
Yeah.
accuracy, it may be improving or not improving, but my question is like what exactly is the data to the each batch?
Right.
Is it
So
randomized or yeah?
no, so I'll tell you what is going on. So let's focus on this training data, right? So forget about validation and test that appears. Now this training data, you're dividing it to small batches. Okay. So this is mini batch 1, mini batch 2, and so on. Okay. Now the common notion is the following. So at epoch 0, suppose I have, say, 2-layer neural network. Okay. So that means that I have W1, W2, B1, B2. And now there is 0, 0, 0, 0. That means these are the values at the current iterate before training. So how would you start? For example, you start with some random initialization, right? So draw entries from Gaussian distribution, randomly initialized, right? So that is the 0th W, right? Initialization. Now, first epoch, you process mini batch 1, you do one update. Now there are, say, 100 mini batches. Now, every time the new to current, you would do all this. Okay. So once you parse your entire training data once, that completes the first epoch. Now, second epoch, you go again back, revisit the data, right? You cycle through the data one by one. So now, at this point, the W that you will use is the W from the last iteration of the previous epoch. You're not reinitializing W.
Understood.
Okay.
Got it.
So you keep on doing this, right? That is what happens. And since you're doing this iteration many times, that is what leads to decline in the loss function.
Understood, because the weights are getting
Yeah, you are
propagated from
updating the
between
weight.
epochs.
Yeah. So for example, like if you only see the first set, okay, random is not tuned for that particular task. So it can give you a very high accuracy, right? Now, the next epoch, okay, you have seen a part of data, you have seen what you want the model to do through the loss function. So that slightly decreases. So once you see that many times, you get to improve. Now, if your loss, you start with some random initialization and your loss is not declining. What that means is there is some problem in the network. Because if your what you had for the random initialization is more or less remaining constant after you do like 10, 15 epochs, then weights are not being updated. It stays random. Right?
So whatever the random variable we give while calling the API, it is for chunking the data only, right?
This initialization?
Yeah, maybe initially whatever we give the random seed
Hmm.
while training to get the repeatability, that random seed will basically reflect in the data chunking and the initialization, or
No. So
only initialization?
one random initialization, you would give one of this curve. Okay. Now you do the second initialization, that's a second seed, you would get some other curve.
Okay.
Okay.
For
Now
weights only.
third
No.
third initialization, you get this. Now, what this is giving you is how sensitive is your model to different initializations. So one initialization will only give you one curve. Okay,
So
now
no
what you
relation.
do is you report the mean and the variation using these many curves.
So nowhere we are actually shuffling the data
Yeah,
between
so
the
now, so this is to measure how sensitive is your model to weight initialization. Now, this is giving you, say, 10 curves. Okay. Now, that is with one shuffle, one particular way of ordering the data. Now, you repeat the same exercise by randomly shuffling the data. So that is going to give you one more curve. Now, for that shuffle, you can do many more weight initializations. Right? So now you're getting hundreds of curves. Now you report the average. Now, typically what is done is whenever we say k-fold cross-validation, you don't initialize the weights, but you shuffle the data. Right? So the that is under the assumption that your model is not sensitive to initialization of weights.
So that
Okay.
weights can be tweaked only with that seed.
Weights can be only tweaked. No, so you pick a seed, and every time you call, you get a different realization of that seed.
Okay.
So every time you initialize, you only initialize at this point. Okay. So that means that for different curves, you can use different seeds. So that means that W0 for all these curves, which means that for first shuffle, you have a W in it at iteration 0. You do a shuffle, iteration 0, you have another in it. Okay, so that in it might be different. So it is the same random number generator, but you're drawing a different realization.
But it will not affect our model performance.
The hope is that it should not affect. Right? So it should be insensitive to the weight initialization. It should be insensitive to the data order. Okay.
So how to check whether it is sensitive to weight initialization?
Yeah, so through these experiments.
Through
through experiments,
yeah.
right? So now, for example, like you say you do first weight initialization, you would get like a loss of 10 power minus 5. And the next initialization, you get something like this, which is not good, right?
Okay.
Okay. Okay, so I don't say the order, but I go Maurya Raj, excuse me if I get the name wrong.
Professor,
Krishna Treya.
The function that we use for the hidden neurons and the output neuron, is it the same or we can make them different?
Say your question again.
The functions that we use for the hidden neurons and the output neuron, are those the same functions or can it be different?
Activation function.
Yes.
Yeah, so activation function. So as I told, it's very common. Although in theory it is possible, but none of the libraries allow this. That for all the neurons in a particular hidden layer, you use the same activation function. But
But
across different hidden layers, you can indeed choose different activation functions. So for example, like, okay, here you could use ReLU, here you could use logistic. That can change. But all those 300 neurons in that hidden layer, you would use always ReLU.
so if we use 50 different hidden layers, so we have to define it 50 times like this?
Yes.
Okay.
Yeah, I mean, you could do a repetitive one or maybe a smarter way, right? So you could basically use some kind of a concatenation, some smarter coding, but naive is this one.
Okay. Thank you.
Okay. Sophia?
Yeah, sir, I have a question. It's very might be silly, but what are non-trainable parameters? Like we can see input, then we have hidden layers output, and everything is included in trainable parameters. So which are non-trainable here? Like not here, but if any other example.
Yeah, so non-trainable. For example, like okay, the output could be like between say you're using say for example a tan hyperbolic, which is
Yeah.
or some ReLU, which is going to
Right.
give you an output which is positive.
Mm-hmm.
Now, related to maybe what somebody was asking Rupesh, that okay, the house price, we know that it will not be between 0 and 1 rupee, but it will be, say, between 1 crore.
Yeah.
Now, what you do is you artificially scale the last layer output with
Correct.
some number,
Yeah.
and that number is fixed. That is not trainable. So all those trainable parameters are those which for which, with respect to which we'll have to compute a gradient and do this gradient descent. So
Uh,
the parameters, trainable parameters are things that are not known to us. Non-trainable parameters are parameters that you say fix it
Okay.
or it is predetermined. So you will see this later. For example, when I talk about towards, hopefully, if time permits, towards the end of today's lecture or the beginning of
Yeah.
next lecture, that it is common, for example, like especially in the current times of large language models or in all these ResNet, ImageNet models, that companies have trained on large compute and large examples some of the models that we cannot compute with the limited resources that we have. But
Right.
what we can do is we can simply download that model and then
Mm-hmm.
add a few more layers to fine tune it for our particular task.
Right. Right.
So in that case, the what non-trainable means is that don't change anything that say Google has already trained. So those W's and B's you fix. Only
Okay.
the W and B that I add, for example, I add one more layer. So that you
Mm-hmm.
train.
Okay. So
So it could be weights and biases that we ask the model to fix, or
right.
it could be some deterministic scaling parameters that we use to make the output more meaningful for the task at hand. So those are non-trainable ones.
So basically, you have said mentioned two things, and the non-trainable is a contextual thing, right? One is when the output value is fixed and we're not changing anything. Let's say house price at 1 crore, you have fixed it, right?
Hmm.
And another one is we're using an existing model and we're not touching the existing hidden layers. We're just adding new hidden layers for our benefit. So
Correct.
these
Yeah.
two are
So,
different contexts.
yeah, different purposes where you would see this non-trainable.
Right.
Right. So that is so for instance, yeah, that the second one is actually called as pre-training, right? So if you
Right.
use a pre-trained model, like a large language model, you simply download, it's already there. But now I need to adapt it for the task at hand.
Okay, sure. Thank you. Just one follow-up, sorry. So when we are predicting the value, let's say house price now before scaling 0 to 1, we are predicting, right? Some regression value, let's say, within 0 to 1 or any number for that matter. So that will be part of trainable. But then when we are scaling it to crore, 1 crore or 2 crore, then that will be non-trainable.
Correct. Yeah.
Oh, thank you.
Yeah. Okay.
Thank you, sir. Yeah.
Yeah. So Imut.
Yeah, hi, Professor.
Hi.
My question is how do I know if the neural network which I have trained, whether it has vanishing or exploding gradients?
So I wanted to discuss this. So can we postpone this to say after the break, like towards the second half of say when we end this class?
Yeah, sure.
Yeah. So to answer your question, the vanishing and exploding, I mean, so this is what typically happens, right? So I'll answer in one sentence, but I would like to come back to this whenever time permits, either today or in the next lecture. So whenever we are computing these gradients, we have a lot of these products. Okay. So now, whenever we have many products, two things happen. One is that you're multiplying small numbers, right? So for example, 0.1 times 0.1 times 0.1 times 0.1, that becomes very small. So that means the value itself is vanishing. Okay. So what that means is, if the output is small and you're multiplying small numbers, that's shrinking to zero, that's vanishing. The other possibility that could happen is you're multiplying numbers that are large, say 2 times 2 becomes 4, 4 times 2 becomes 8. So you're exploding. Now, although we said that the activation function that we have uh, is kind of smooth, has a non-zero gradient, but if you see that non-zero gradient only happens in the shaded region and not in the saturating regions. So when I have these large numbers, so for example, you have these products and the output becomes, say, 10. In that case, if you look at the sigmoid function, it is again very similar to the step function where the gradient, there's no gradient, that will be 0. So even for this nice activation function, the reasonable operating range is the shaded region between -1 and +1 that we have to maintain. So whenever again at 0, whenever you have a 0 input, the output is 0 clearly, right? So these cases, you don't have the gradients that are desirable. So these are the two cases where you have vanishing and exploding gradient. Hope that answers your question, but I would wish to come back to this at some point during this module.
No, sir. My question was that uh,
Now, how would you check?
Yeah, how to determine if my network already has this?
So now, okay, you understood so most of you, I guess, understood what vanishing and exploding gradients are with this simple illustration. Now, how to maintain this is what we will cover. But now, as I already mentioned at some point, right? So, okay, maybe I can do that. That's simpler. So, for example, you're, say, working with the regression problem. And what happens is that you initialize, say, at iteration 0, you initialize the weights and you have a loss of 10 power, say 10, some number MSE 10. Now you see that as iterations progresses, either the loss is not decreasing too much. Okay. Ideally, you would expect that this becomes at least like 3 orders or 4 orders lesser. That is the MSE that is desired. But you see that it is not changing at all. So here, what would that mean is that you're not doing some normalization properly, right? So this could be an example of a vanishing or exploding gradient. This need not be around 10, but for example, this could be like, say, 10 power -1. So you want it to decrease further, but it is not decreasing. So this is one classic way of checking if you have vanishing or exploding gradients. Okay. And the other way is, so the other way is to look at, there are these weights and biases analysis tools where you see that the weights that you train, you can measure what is the size of the weight. For example, you can measure the norm or the energy of the weights, right? And then you see that the energy is very large, right? So if the weights are, say, of the order, you initialize with, say, somewhere in, typically all the matrices have numbers 0.1, right? So for example, now you see that layer 3, layer 4, they have weights of the order 10 power 3 or 10 power -5. Either it is shrinking or it is exploding. Then what that also means is that is leading to the saturation. So you could do a tensor board analysis of weights and biases. So you just look for weights and biases toolbox. You see this. So these are typically the ways to check if you have vanishing and exploding gradients. Okay.
Yeah. Thank you very much.
Okay. So yeah, I guess I already answered Rupesh's question that, okay, you do some scaling depending on the task at hand. Okay. So Now, what we will do is we'll pause for a break, resume back, say at 11, and continue with the discussion. But we now look at a particular specialization. Krishnan, how do we initialize weights? For now, imagine that we do that randomly. But as I told, like I would like to discuss those 2, 3 slides whenever time permits, either today or in the beginning of next lecture, right? So there is some more logic behind that, which I would like to discuss. But for now, imagine that you can do that randomly, which works 70% of the times. Okay, so now let's pause for a break and then come back at 11. Okay, so let's resume. Just one question that I think was left over. So do we reset the, I guess you mean the weight vector every epoch? No. So only in 0 iteration, that is the initialization. So when we visit back, you use, as I said, the weights from the last iteration of the last mini batch, right? So only 0 epoch, the weights are initialized, and then you keep on reusing the weights. Okay, so I hope everybody is back. Now let's switch gears and discuss a specialization, I would say a specialization of MLPs, but for structured data. So far, we had a matrix which could be potentially an image where the columns are features, but there's no relationship that was exploited between the features. Now, whenever there is a relationship, how do we account for that? And what is a consequence of using MLPs for such tasks? So convolution neural networks are predominantly used for images, but you can use them for time series data. So here what you basically see is a time series data from, it's an audio recording of 2 engines or automotive engines. One is a faulty engine with some knock, and the other one is not faulty. And the goal now is to classify based on audio recordings whether there is a fault in the engine or not. So this is basically for diagnostic purposes of any machinery, right? So fault diagnosis. So automatically do fault diagnosis. You can use it for speech beyond images, right? That's the main point. The typical downstream tasks that you will often use with convolution neural networks is the same, for example, as classification or regression. For example, by looking at this time series data, you would like to classify whether it belongs to class 1 or class 2, whether you would look at this picture and put a bounding box, which means that what we require is 2 boxes. The first box is kind of a feature extraction. And then once you have feature extraction, you basically have some kind of a classifier or a regressor, and you will often see that you would still use an MLP at the end. Okay, so the feature extractor is typically the convolution neural networks. So the way you see that is you have many layers of neural networks. The initial layers are convolutional layers. Towards the end, you would have a multi-layer perceptron that is actually solving the downstream task of interest. For example, the downstream task would be to put a bounding box against these flower buds. Or the often utilized task is the task of segmentation, where segmentation is very similar to classification, but you're not classifying the entire picture, but you're classifying every pixel of a image. For example, what we have here is many objects in that image, right? So there are cycles, there are cars, there is a sidewalk, there is a road, etc. Now you would like to make classes for each of them, right? So that is basically segmentation. So you would like to classify this as a person. This is the sidewalk, right? So these are different classes. Each pixel needs to be classified. So, but here, recall, unlike the tabular data setting, I'm not telling any feature, right? So like, okay, if the object is this much wide, this much tall, has this color, this could be a person. That feature I'm not giving. What we need to do is to have a black box that is automatically extracting features that are relevant for the task at hand. So you do that feature extraction using these convolutional layers. And then once we have these refined features, you still have an MLP that is going to give you a classification or a regression, right? Now, what is the training data looking like? The input data is bunch of these images, and the output data is, for example, like this, right? So that's the labels. So you would have this as X and this is your Y. So that's the training data. You have many of these training examples. Once we have these, in the test case, I would just output such a picture, and then it's going to classify into one of these predetermined set of classes. Similarly, for this bounding box localization example, I would show many examples, right, with bounding boxes. That is the input output pair. The input is the image. The output is that boundary, the black or the red box. It could have one bounding box. It could have many bounding boxes and so on. It could have bounding box plus label, right? So you might have seen this illustrations in many examples, right? Okay, you're looking at pedestrian and then they are tagging different objects as vehicles, person, and to an extent even beyond like facial recognition to name of that person, right? So bounding box could be much more carrying much more information. So those are the input output pairs. Except that now I'm not giving features, but I need an automatic feature extractor. Okay. So in order to solve all these tasks, we use convolution neural networks. Any convolution neural network architecture would have this particular format, a set of neural networks, which we call as convolution. We'll see what that is. And then MLP towards the end. MLP will always be there, right? So that's lecture week 1 or whatever we studied so far. That is very important. Doesn't matter what task we do. Okay. Now, you might always wonder, why do I require these new convolutional neural networks? While potentially we already solved this classification problem with images, this 20, although 28 by 28 pixel images, that was an image. What we did was simply vectorizing that and then feeding to a neural network. Why do I require this? Why do I require a newer architecture? Now, to answer that question, you have to see what are the typical images and how often do we see an image that is 28 by 28 pixel, right? So 28 by 28 pixel is not even like 1000 pixel, right? So that's not even 1K pixel. But most of the cameras that you see nowadays are 12 to 24 megapixel, outputting color images, not these grayscale images. So what that means is the data that we see is completely out of proportion, right? So compared to this MNIST image. Now, even for a single layer perceptron model with 100 neurons with 784 pixels, we require about 784K parameters in the first layer. Now, applying that same logic, vectorizing at 12 megapixel color image, which basically amounts to 36 megapixel because of the red, green, and blue channels, RGB3 channels that appear in an image. So you have 36 megapixel. 36 megapixel, you vectorize, feed it to a perceptron, a single layer perceptron, which is practically useless for large realistic applications. So you get about 3.6 billion parameters. Okay, so I hope you're able to get the sense of what that basically means. We are not even going to the first hidden layer, the second hidden layer. So just the first layer, you have 3.6 billion parameters. Okay, so now just to quickly convey the sense of the essence of the problem, let's take this question to see what is the memory that I need to allocate just for the first layer. Okay. So 12 megapixel, beautiful camera that people are taking pictures around, and you would like to train a model, right? So for face recognition or whatever task you have. So what is the memory that you think you need to accommodate? Okay. With this particular data type, flow 32, right? You could use something simpler, but the essence is not to say I can do something in a simpler way. But if I use a default setting, just to get a sense of what is the GPU size, we're not even, this is just to load initialize the parameter vector and load one image, not even a mini batch. Just wanted to let you all think for half a minute, and I'll end this poll soon. So of course, the goal is not to get the answer right. I mean, if you do a bit of Google search, you would see that this particular data type requires float 32 4 bytes. You do 3.6 times 4, you would see that just to load one image, waits for that first layer with 100 neurons, you require 14 GB. Now imagine 32 times a mini batch of this, multiply this by 32, and then you have at least like 4 more layers, each with about the same parameters. Just to train such a model, you require a GPU close to 100 GB. And clearly, there are models which give you very good accuracies without such a load on the computational requirement. Now, how do we achieve that, right? That is what we will discuss in the rest of the lecture. What is clear at this point is MLPs are not suitable, readily suitable. I still cannot get away with this MLP, but I need to somehow adapt this logic of composing many parametric nonlinear functions. So I do features, linear transformation, apply nonlinearity. Repeat that many times. And if I do that, I'm going to get something very nice. That is what we have appreciated so far. But that seems to be blowing out of proportions as far as parameter size is concerned. So I need to somehow curtail that. How do I do that? Okay. To do that, what we often do is we draw inspiration from what most of the images look like, right? So we again recall most of this artificial neural network, artificial intelligence is built around mimicking nature. Nature could be a human, or it could be how nature appears, right? So to do that, we use something known as a local receptive field, which is how most of the vision, human or any vision sensor would work. And that basically exploits the fact how most of the natural images appear. If you look at any natural image, which could be this cartoon, which basically tells one very nice fact. If I look at locally any image, those pixels are correlated, right? So if I look at two pixels that are close by, nothing much changes. But as I move far away, there is some change that is happening. That is called as a local receptive field. Similarly, any image that you appear, right? So anything that you see around yourself, nothing much would change given the size of that image. If you look at small regions, nothing much would change, right? If you look at any whatever is seen in front of you, that particular local receptive field, nothing changes. If you look at the image of this tiger, within this region, nothing much changes. But if I go away a bit further, there is something change happening. So the point is, nearby pixels are more correlated than pixels that are far away. That is a phenomena that appears in most of the naturally appearing signals, right? So for example, if you look at the signal of a speech, and if you look at a certain time window, nothing much changes naturally. Nothing much changes within that small window, but over a larger horizon, things change. If you look at, say, for example, data of a currency, right? So INR versus USD, for instance, if you look at over a certain window, nothing much changes. But over a larger window, there might be deviation. That is how most of the natural signals are. Now, if things do not appear that way, it is not very pleasing. Most of the things are not interesting. For example, if things are fluctuating very fast. If I see an image where nearby pixels are also changing very fast, then that would basically amount to noise, and we would not be interested in doing analytics of noise. Most of the natural images appear this. Now, how do I use this particular concept of this local receptive field to design my neural networks? And that is what CNNs adopt. Okay. Now, we will see what that is. But before that, let's do this nice exercise. And this is a version of a problem many of you might have seen in different Indian versions of this picture when we were kids. The goal is that there is this particular character whose name is Waldo. Now, what I want you to do is I want you to look into this picture, which looks very cluttered apparently, and figure out where Waldo is. And we'll do that for half a minute. And then I let a couple of you tell me where would you see this picture of Waldo in this picture on the right. And then what I also want you to do is a couple of you to let me know how did you process that, right? So what is the algorithm that you use to figure out where this is, wherever you figure this out. Okay, so take half a minute to do that exercise, and then we will connect. So I want this person is somewhere here. In the picture. There could be some misleading information, but your job is now to let me know where is Waldo, right? So this is a famous game like Sudoku, but yeah, there are like many of these images. You have to figure out where the character is, right? So many of you might have seen a version of this with a different character, maybe. Okay, so I hope at least a few of you have figured out where this Waldo is. Okay, so what I'll do is if a few of you want to respond in the chat, feel free to do so. I will now just pick a few of them to let me know what is the algorithm that you use to process it. So I will go behind, yeah, with the, yeah, I think I just go with names. Aditi Ravishankar, right? So let me know. Please unmute yourself and let me
Yeah.
know what is the algorithm that you used.
Yeah, Professor. So from the bottom, I just went from left to right. Like I kind of divided this into a grid vision, like in my mind, and just went left to right, searching for the t-shirt pattern. And when I found, I checked for the hat. If it wasn't there, then I just proceeded, like going to the right, and
Okay,
yeah,
thank you.
and then eventually ended up finding
Mhm.
what. Yeah.
So maybe I'll ask one more person. Like I see, yeah, Rupesh.
Yeah, similar search, Professor. Like I was just scanning from left to right for the similar patterns like
Okay.
t-shirt strips, whichever are there. So
Mhm.
just checking for the pattern. If it is matching, yeah.
Okay. Okay, very well. So whatever Aditi and Rupesh just now described is convolutional neural networks in English. So what that means is like we can also wind up today's class and then enjoy rest of the weekend. But that's precisely what CNNs are doing, right? So this is a natural way to process. But now, jokes apart, we will not let you go so easily. We will go through what is the math behind it. So precisely what we do naturally is convolutions. People might have with an EE background might have seen what convolutions or correlations is in their signals and systems class and might have struggled, but in simple words, this is what convolution is. So what you're basically doing is I want to now divide this image, large image, 36 megapixel, 46 megapixel, doesn't matter. Why are we dividing it? Again, local receptive field. That's how humans are naturally trained, because I can process any large data, but whatever memory we have, right? So whatever capacity, people have quantified that or not quantified that, that is kind of limited, right? So I don't have like, I might have infinite, but there is a bound on that, right? So what we do is we divide whatever data we get into smaller chunks, and you process that, right? So Aditi is telling that she's going to systematically go from one way to the other. Very good. Someone might just go randomly, right? So that's how their thoughts are organized. There's no good or bad in that logic. So there is some fixed window you're always looking at. Either you follow a convention, a systematic approach, go from left to right, which is called as a raster scan, or you randomly search to figure out a pattern. And what are the patterns that you're looking for? Okay, maybe a hat, maybe the striped shirt. And whenever you see that, okay, there is a trigger, right? So you say, I found this person, right? So that is basically what you're trying to do whenever we see such images. And this is what you would want your computer to also mimic, right? Why is it, what is it helping you? You're not processing all this large image, which could be very large, like 12 megapixel means you have like the image area increases, number of pixel density increases. But if I now choose a fixed window, I can do so based on whatever memory capacity I have, right? If I have like a 14 GB GPU, now I only process that part of data at a given instance. Now I should extract features by looking all over the image and then do something to solve the particular task at hand. Here, it was like put a bounding box around Waldo. That is what we were trying to do. It could be something else, right? So it could be a simple yes or no answer. Is there a Waldo in this image or no Waldo in this image, right? So that could be few tasks related to this image, but now you could use computers to basically mimic that algorithm. And that is called as convolution, right? So now what is convolution? Uh, I have two technical terms here. Convolution, what is actually done in signals which are causal. What we actually do in convolutional neural network is called cross correlation. But we see that, okay, there is similarity between convolution and cross correlation, but colloquially, it became popular as convolution neural networks, not as cross correlation neural networks. But anyway, so not getting into that detail, what would you do? What in practice? So I have two signals here, F and G. One is of a square pulse and the other one is a triangular shape pulse. What we do is, like what most of you would have done, is I'm going to slide one signal over the other. So I'm doing that slide starting from this point with some steps. I'm doing a scan. Now, when doing a scan, what I do is I see what is the overlap, right? So I multiply the area-wise overlap and report that. So for example, here there is a 0 overlap. At this point, there is a small overlap, so the signal level increases. But at this point, okay, there is significant overlap. There is a area overlap increases, so the signal level increases, right? So now what that basically means is that, okay, the signal G and F are slightly correlated. When the signals are kind of orthogonal to each other, there'll be no overlap, right? So that is what is done. Now, if F and G were basically same, then that peak that you would get would be more. Now, for instance, if you're looking at a simple classifier, not like a complicated MLP classifier, you can just put a threshold to see that, okay, if there is that particular content there or not, right? So this is simple words, what you would do. Now, pictures are more complicated, not as simple as this. Like, okay, Waldo has much more things. The task could be more complicated, but the idea remains the same, right? So now, the slight difference between convolution and correlation is that you do the slide, measure overlap, slide, measure overlap, report, right? So that's a simple logic in English. Math, that's called convolution, right? So you pointwise add, pointwise multiply and add, right? In convolution, the slight difference is that the second signal is flipped and then added, right? So that is the subtle difference, but otherwise, pointwise multiplication and addition remains the same. For example, in this case, the signal is kind of flipped, right? So it becomes like this, and then you do a flip of that signal and then do pointwise multiplication and addition. This is convolution. To be more precise, what is actually implemented in convolution neural networks is cross correlation, right? But ignoring the difference, understanding the main message, whatever Aditi and Rupesh explained, that is what is going on in math. Now, I would like to get features that would enable these tasks. I want some adaptability. I want to do this using a perceptron, right? So this is what we need to keep in mind. How do I do that, right? So that is what we will see in what follows. Now, keep two things in mind. One is that there is some structure in the data that we process. Nearby pixels are correlated than the faraway pixels. And I need to do some kind of feature extraction, okay? So now, to do that, what we do is the following. We drop a few connections in the MLP. So in the MLP that we saw before, you see that every neuron is connected to every other neuron, right? So that is the basic model that we saw so far, multi-layer perceptron. Okay, so this is connected to this, and this. So is every other neuron. Now, when I'm interested in local receptive field, what that means is from one pixel, as the pixel distance increases, I need not combine those features. I can ignore those connections. There is nothing to combine because they're not related. So what I do is I basically restrict myself to a local receptive field. I have those, but then the arrows that go from here to here and the weights, I drop them. So every time I'm looking at a particular small patch of neighborhood, now what you do again is I reuse these weights. Okay. So I look at a patch, learn something. I now look at another patch with the same set of weights, because whatever is being learned in the small patch is the same. You're looking for the same set of features, right? So what is not known is W1 and W2 as before. Okay. Now, this illustration, you should imagine this as a time series, right? So you have like time 1, time 2, time 3. We will see how this is done for images with a nice set of animations as we progress. But the point is, now if I choose a fixed set of W's, for example, if I want to see if there is an edge in the image, I can choose W to be 1 and -1. And here you would see it acts as an edge detector. This is kind of hard wiring these filter weights, but we would learn these as we progress. So for example, whenever the x is different, right? So then I get a non-zero value. Whenever the x's are the same, I get a 0. So it's going to detect some kind of a transition. That is what the edge detector will do. But here, there is nothing to learn, right? We already fixed W1 and W2. But now I can do the same across images to see if there is any transition or not, right? I hope you get the idea. So now let's formalize this. This operation is called convolution, right? How do we do that, and what do we get is what we will see. So as I said, formally, this W1 and W2, the weights that we were calling weights in MLP, is now called as a filter. Okay, the filter, you have the same set of filter, W1, W2, W1, W2, W1, W2. You have one filter of size 2. And what this is basically doing is, at this point, it is doing x1, x2, x3. These are our features. Okay. So here you're doing x1, w1 plus x2, w2 with some non-linearity. That is what is coming here. So here you're doing the same thing, x3, w1 plus x4, w2 and some non-linearity, right? So it's very similar to the logic behind MLPs, right? How we evolve with MLPs. But two things, we are using a local receptive field looking at a certain window. So this could be, for example, a time series signal with time window 6. So you're looking at a particular portion, combining with some weights, reporting it to the next layer. The next layer, you do the same thing, right? So it can be a local receptive field till you have enough layers of convolution, and then you do an MLP. We'll see that later. So here we have one filter of size 2. Okay. And we are doing parameter sharing. What that means, I'm using a set of weights. So now if we step back and see what is going on, all the, irrespective of the size of the image, 12 megapixel, 24 megapixel, the weights are under our control. The weights is not exploding. The number of weights, that are number of trainable parameters, are not exploding. And what we are doing is we are extracting features from the input data. Okay, so this is 1D convolution. Now, let's take a poll to basically get this contrast that I was emphasizing so far. And then proceed further. So when do I need to use CNNs compared to MLPs? And do I need to do that only for images, or can I do that for 1D signals? So this is all we need to keep in mind. Right. So that's the essence or the message that I want to convey with this particular report. So It's a simple exercise, so I'll not spend too much time on the poll itself. And I'll end that now. Okay. So clearly, whenever there is some kind of an ordered relation between pixels or ordered relation between time instances, then I can reduce the number of parameters and use convolutional neural networks. Again, although CNNs are super popular for image and vision applications, it's not necessary that you limit yourself to images, but you could do 1D through this 1D convolution or even 3D volumes, right? So that could be, for example, like in case of a volumetric imaging that is common in medical field nowadays, like either 3D ultrasound or PET scans, etc. You would use a 3D convolution. Now, what we will do is we will develop our understanding for a 2D convolution and all the building blocks that go into the convolutional neural networks. Okay. And you will see that it is, well, when you have to program it, it's very similar to what we did so far. Instead of MLP or a dense layer, I'm using a conv 1D, 2D, or a 3D. The remaining things are the same. So you basically sequentially put many convolution layers and so on, but we will see as many blocks as possible that we can cover today, and then we will continue discussion on that if required in the next lecture as well. Okay, so that's the basic plan for what follows. So Piyush, if you have a quick question, I'll let you ask that. Otherwise,
Yeah, just a quick one. So I've typed it in as well in the chat. So when you say filters, are we reusing weights? Are we only focusing on a subset of a feature and reuse the same weights across the different neurons and just work that out in a particular layer and then go on to the next layer and do the same
I
thing
will,
for
yeah, and then that's what will follow a bit more in detail in the next slide. I'll answer. I mean, it will be
Okay,
clear.
thank you.
Okay. Okay. So now, yeah, so the plan is we'll look into 2D convolutions and some of the other aspects as we progress, and then hopefully we'll be able to put them together as a CNN at the end of today's lecture. If not, we will continue, right? That's the plan. So this is a cartoon animation of what is going on in a 2D convolution. So imagine we have an image. The dark blue layer is an image. The green one is the feature that is extracted after a one layer of convolution operation. Here, there is no nonlinearity, and the filter weights that you see in the matrix here is kind of fixed here for us to understand computation. But in practice, you will be learning these weights through backpropagation, and you would be learning them through gradient descent, right? But for the sake of illustration, let's assume, how do we do that forward pass? So now I have an image, okay? So some more details will become clear as we progress, but for now, like what Aditi mentioned, we're going to fix a convention of a raster scan. And that convention typically is I divide my pixels into certain size. What size, etc. Let's not worry about those details for now. But what you see is the following. I have divided my pixels into subsets. And then every time I'm going to do a raster scan. Okay. Now, in each scan, what do? I basically do a pointwise multiplication and addition to get this particular value. Okay. So now I repeat that operation for every stride that we do. So stride is basically a walk length, right? So how far I walk. Right now I'm going 1 pixel stride. So I have 3 by 3. Now I hop 1 pixel, go to this. Okay. and I'm fixing the size of the filter. How do I fix? What should I use? It's a hyperparameter. Let's not worry about that. Now, for this particular illustration of doing this convolution, so I do this many times, I get the feature map. Okay, one operation. In practice, you would use nonlinearity and so on, but we have computed this feature map. Now, how do I compute one entry of this feature map is what I'll discuss next. So suppose we have this image, which is 3 by 3, and those are the entries of this image. Okay, some entries. Now, the filter, either with initialization or some iteration of your backpropagation, these are the values. We are using a filter of size 2 by 2. Okay, filter is also often called as kernel. Okay, they can be used interchangeably. Kernel or filter, they mean the same. So now, what is going on? First scan, I do 0 times 0, 1 times 1, 0 times 0, 1 times 1, 3 times 2, 4 times 3. I add all these numbers. I get 19. Okay, so that's the first value in the feature map. Next, what I do, 1 times 0, 2 times 1, shift by 1 pixel, do pointwise multiplication and addition, I get 25. Repeat the same, 37 and 43. Okay, so that is basically the output. Now, how many outputs we get depends on the size of the image, the input, and size of the kernel, size of the filter. And the computation is straightforward. So if I have, say, 3 by 3 and filter is of size 2 by 2, the output of the feature map is 3 minus 2 plus 1, right? So that is what 4 minus 2 is 2. So I get a 2 by 2, right? So you can basically compute what is the size of the feature map using this simple formula. Now, you can do the same for this particular image, which is 7 by maybe 7 by 7, and then the size of the filter is 3 by 3, you can compute, right? So that with particular stride and all, we'll see what that is. But a simple operation of a 2D convolution is the following. So now if you look at what is this convolution, this is again a linear operation. And in practice, you will also have a bias. What is important to notice is that I'm replacing the multiplication with the star, which is the convolution. It is again a linear transformation plus bias. But if you look at what this means is, this is using W in a certain repetitive fashion. We are doing parameter sharing when we go from one scan to the next scan, one hop to the next hop. Okay, so this is 2D convolution. Now, all these questions we will answer, right? So what happens with RGB, etc. You have an image, you do the same thing. Image, you will not have this 2D structure, you will have a 1D structure, right? So you would basically do again a pointwise multiplication and addition, okay? And it is good to get a sense of what is the output size, but the formula, as usual, you do a simple command line, you can get what is the size of the features and so on. So input becomes a feature map. You're extracting features. Okay. So now these features, how you extract these features, right? What is the filter entry that we need to use? That depends on the task at hand. Maybe for the task of detecting whether there was a wall or not, you would use different entries in the filter. You would learn different entries. If you want to put a bounding box, that could be different entries, right? So that's the main message. Now, what is important to see is the following. With this simple 2D convolution, I can extract very nice features. For example, I can basically not do anything but subsample an image by using an identity filter. Or by choosing certain set of weights, I can figure out what are the edges, the boundaries in the image of this, whatever this animal is. I think this is, I don't know, a camel or a kangaroo. But Using some filters, I can extract features. And oftentimes, what is also important to keep in mind is just extracting one set of features might not be relevant. For example, if you see this building, I have two sets of filters. So these are again like hard-coded filters just for the sake of understanding. So this building, a Chinese architecture, we'll see this image later on in a few more slides. We see that this consists of many vertical lines and also horizontal lines. So we might want to extract many such features, which are the basic building blocks of an image, right? The basic features. So oftentimes you would not use a single filter like what we use here to extract a feature map. But then imagine that I have many such filters which will extract many feature maps. And to see why is that needed, you see that, okay, if I use a vertical filter, it's going to filter all the vertical lines, give you some set of filters, basically breaking down how this image is formed, right? So what are the basic features that synthesize that image? Could be a lot of vertical lines, a curved line, horizontal lines. The horizontal filter is going to extract all these horizontal lines that were there in the picture. So message, feature extraction is happening via this convolution operation. We are restricting the size of the filter, hence the number of parameters. I don't have to worry now about how big the image is because I'm breaking down that into smaller chunks. I do the same thing, 12 megapixel, 24 megapixel, I don't care. So I don't have to worry about the size of the memory that is exploding or the size of the GPU that I need to purchase. I can basically work with whatever GPU that I have with some additional latency, right? So instead of processing larger data, I now process smaller chunks, but many times. Okay, so many feature maps are required. Why is that so? That is because, again, drawing inspiration from nature, that is how we process image. This is again a very nice illustration of what is going on, right? So now, if you look at this image, or for example, like how kids typically learn how to write strokes, right? So you maybe you recollect from school, or at least like nowadays how kids are learning standing line, sleeping line, vertical line. So that is the basic structure of any image or any letter that you learn, right? So then, okay, you start introducing slopes, etc. Those are the basic features that basically are constituent in any image. So for this cartoon of a house, we see that, okay, it has a bunch of these vertical lines and then bunch of slopes and so on. Or if you want to construct this fish versus, just for illustration, might not make any sense, fish versus house classification, what you would like to do is extract basic features. Okay, that is how our human brain also processes whenever we see images. You extract basic features. Okay, there are these basic lines like the basic curves, circles, lines, and so on. And then those are synthesized together to make something more complicated, like a triangle and this whatever cross, etc. Again, that becomes a bit more abstract to form an image. So now, what that basically means is I need to extract all those basic features as possible. And that is what is typically done in a CNN architecture as well. So we have an input layer, and that input layer, you do convolution. This convolution layer, it could be implemented using one filter or many filters. So you get a feature map, many feature maps. Now you again process that through another convolution layer, or again, it could be a single filter or many filters that is going to give you another set of feature maps. So we keep on doing this. So what that basically means is I have now an input image. I do a convolution with one set of filters, apply nonlinearity, again do a convolution another nonlinearity, and you keep on doing this, right? So this can be repeated. But we just don't use one particular filter, but we can use many filters. Okay. So now, what is the disadvantage with this, right? So I need something more, but what is the disadvantage just by using convolution? And that is this poll question that is related to the size of the feature map. Okay. So I have a 32 by 32 image. Now I keep on doing this convolution operation. Okay. So because I want to extract as many features as possible, I go deeper into the network. Now, what is the size of the output, the feature map? If I use a 5 by 5 filter after 7 layers. Okay. So I'm basically cascading, right? So here in the cartoon, you see 2 layers, but if I keep on doing 7 layers, what is that we get? So that basically means that we simply have to keep on applying that formula 7 times. Okay. And you will see what is the problem with that if I keep on doing that without doing something smart. Okay, I'll end this poll now. Okay, I hope all of you did this iterative unrolling of the iterations and the computations of the numbers. So if we have a 32 by 32, recall it is NH minus FH plus 1. So that is going to give some number, right? So this is 33 minus 5 is about 28, I guess. Then you do that again. So you keep on doing this 7 times, right? So you end up with 4 by 4. Okay, so I see that many of you have got this all right. The main point is, if I'm simply extracting these features, then clearly for this small example of 32 by 32 image and using a reasonably small filter size, I cannot go beyond 7 layers, right? So after 7 layers, the output is now 4 by 4. Now I have a filter that is 5 by 5. Two problems occur. One is that the shape of the feature map is shrinking very fast. I don't have any control over that. The second problem is this could even appear in the first layer itself, but in this particular example, it appears in the 7th layer, is that I don't know what to do when the filter is larger than the image itself. That means that we had a point-wise multiplication and addition operation, but I don't know how to do that for this particular area. Okay, so those are two reasons why we will introduce two knobs. So these are like the knobs of your gas stove, which will allow us to control the rate at which the size of the feature map decays. So the second one, the first knob basically increases, the second knob decreases, right? So this is basically the two features that we will introduce after we have understood this 2D convolution operation. Okay. So are there any questions at this point? Is it clear? Any quick question about understanding? So unordered relation versus Gaurav's question, what is unordered relation versus ordered relation? So in this particular case, the features are basically our pixel intensities. So what we are trying to see is that, is there any structure in the pixel? And the structure is that, okay, if I look at all these pictures, within a particular window, not much is changing, right? So it is basically the same set of green patches, right? Now, the features are kind of structured. Now, contrast this with the petal width length of this image, the flower classification. Here, there need not be any structure between petal length and petal width, right? So maybe there is, but in general, in tabular data, you don't exploit any structure between the features. So that is typically what is called as unstructured or unordered relations. Here we have some ordered representation. Now, what are the two knobs? So these are two features. It's not related to the 2D image, but the knobs basically help us to control the decay. So here we have an image and that image is being reduced, right? So we have an image of size, say NH, it is being reduced by FH. Okay, now I want some handle to not have this size at the output, but have something that is controllable, right? So I give some parameters so that will help me to not reduce after 7 layers a 4 by 4, but it can still retain it to be, say, a 10 by 10, right? So with this, I cannot control. It is kind of deterministic size from input to output, right? Via this 2D convolution operation. So 1D convolution. So here 2D means there is horizontal and vertical 2D. 1D convolution is for time series, right? So there is only time domain, right? So here what you would do as a raster scan, you would visit windows, right? One window, the second window, and so on. Piyush, I guess your question was, I hope it was already answered. And Apurva as well, right? So how do we decide the limit of a nearby feature? So it is what we will see as we progress, but that is kind of determined by the size of the kernel. If I use 5 by 5, I'm basically assuming that the 5 by 5 pixels are nearby, right? So that is the understanding. What to choose 5 by 5? How do I need to choose filter sizes for different convolution layers and so on? We will see as we progress. Okay, now the first knob that I mentioned is called as padding. Padding serves two purposes. So we studied 2D, we understood what is 2D convolution. You already knew what 2D convolution is, but I formalized that through these illustrations and the underlying math, what 2D convolution is. Now we will introduce two other building blocks of a CNN. First one is called padding. The second one, the next slide, we will introduce that. Padding serves two purposes. One is the illustration and the animation that is going on here. Particularly notice when the animation is at this point. Okay. So now if you look at this, the image is of a certain size, but the filter is of a certain size. Now at some point, what will happen is I will have to do a scan of this region. But now the 2D convolution operation only defines a pointwise multiplication and addition over this image. What that means is whenever I'm at this point, I can do processing of this all the way up to processing of this. But then the next stride I do, the way we have defined 2D convolution, I'll have to ignore this. But now what that means is I'm ignoring everything that is happening in the boundary. I don't want to do that. The second thing is there was not control in the rate at which the size of the feature map decreases, but now I have to have a handle. To do that, what we introduce is something called as padding. As the name indicates, you pad the image with some known numbers to artificially increase the size of the image. Okay, and we want to introduce that without changing any meaning to that image. And a simple way to do that is by something called as a zero padding, right? So we pad images with zeros, both horizontally and vertically. Okay, so you artificially extend the image by introducing zeros. Now, by introducing zeros here, the output, what I'm doing is whatever is multiplied with a zero remains zero, does not change the feature map at this point, because multiplying with zeros will not change much, but it is giving me a valid mathematical operation to proceed further. So it is kind of an artificial exercise. But what is that doing? It is now changing the size of the image. So from NH to NH plus PH, right? So depending on how we are padding, it is increasing the size of the image. So what that means is, now instead of becoming 4 by 4, right? So the first was 27 minus 5 plus 1. So this is 20, I guess 28. 28 minus 5 is, so this is 28. I don't know, it was 32 if I remember, right? 32. The previous example doesn't really matter the number. So this is 33. 33 minus 5 is 28, right? So instead of 28, now if I pad zeros, I can make it to 30, right? So if I pad 2 zeros, right? So you get the point, right? So now I have one knob. I can keep on padding at every layer so that the feature map doesn't decay to 4 by 4 very fast, but I have a handle. But even more importantly, I now get to handle what is going on in the boundaries. Now, the operation remains the same. So in this particular case, you see that we have padded horizontal. PH would be 2 zeros horizontal. Similarly, vertical would be 2 zeros. So you have P horizontal, or the width and the horizontal, 2 and 2. So fill operations is the same. So here 0 times anything would be 0, and you get the point, right? So point-wise addition with 0 doesn't change much. But the size of the feature map is now not NH minus FH plus 1, but it is NH minus FH plus PH because of the artificial increase in the size. So 2 reasons which we need padding. Now, the other handle that we would need is, although we kind of took it for granted, is how much I need to hop. Okay, so previously in all this, stride, as I already mentioned, is the walk length. Okay, the padding typically is uniform, right? So again, in theory, if you are not want to use any of the off-the-shelf packages, you can program this manually, but there's no need to do that. There are like efficient functions that people have defined. We will see for carers how this is done in practice, right? So you would not uniformly pad, but padding is kind of automatically decided, right? So we'll see what you don't specify actually the number per layer, but you use with a simpler argument, right? So as you can see, like, although in theory there's a lot of flexibility, I can choose how much of vertical and horizontal padding per layer I need to use, and for each filter I need to use. But instead, you would, while programming, you would like a simple argument, right? So an yes or no type of thing. We will see what that is, how it is done in Keras, and very similar in PyTorch as well. That is what we will see when we look at the code snippet. Okay, so now we have done with padding. The striding is how much stride do I need to use when I'm going from one patch to the other, right? So we saw that, okay, this Waldo, I'm moving from left to right, moving all the way, covering the image. Now, how fast do I need to move? That also determines how fast the filter size, how fast the feature size decreases. So in this 2 illustrations, what we see is that on the right, we have a stride of 1. So I'm hopping 1 pixel per time. So, right. So I start with this. Now I go one hop. That is called as a stride of one. Okay. So clearly I'm slowly, very slowly taking baby steps, right? So that is stride of one. Large strides means I'm covering that picture very fast. So here I'm using a stride of 2, which means that instead of here, I'm directly going to 2 hops. Now, when to use a larger stride, when to use a smaller stride. Now, imagine that you have a picture of a landscape, a beach, right? So beach, calm, nothing else. You would like to put a segmentation of a beach where there is sand and yeah, maybe there is like ocean and maybe there are a few clouds. Okay. So this is the picture of a beach, right? So my cartoon drawing of a beach. Now, in this particular case, what does our common sense tell? Do I need to use a very small stride? No, right? So if I choose a very small stride, okay, I can go very slowly over this, but nothing much is changing from one feature to the other feature after extraction. Instead, I can use a very large stride to cover that image very fast. Nothing much is changing, right? So half the picture is sand and rest half is sea, ocean, and cloud, right? So I can use a very large stride. So these are some of the things that one can choose to trade off between how many parameters that we need, what is the size of the memory that would incur. Size of the memory might not be because of the number of parameters. In both these examples that we see here, you're still using a filter of size 2. But what comes out is the size of the feature map that changes, right? So if I'm choosing a very small stride, the consequent feature map would be larger. Otherwise, you would have like smaller stride. So that kind of all these are mathematically put together to let us program a computer to take automatic decisions. But what is leading to these? It is most of the things that we are doing, what we discussed with Waldo are natural things that anyone would do, right? So, but somebody thought through this process and then put it as a programming, an automated learning mechanism to achieve all these nice results that we can get either with medical imaging or um, uh, as simple tasks as handwritten digit classification and so on. So 2 knobs, padding, stride. Convolution is what is at the backbone of all this, right? So it doesn't matter what padding you use, what striding you use, you are always using convolutions, right? That is what we need to keep in mind. So the stride, you would fix the stride, right? So you would fix the stride. You can change the stride from one feature map to the other. For example, the base image, you're using one stride, but one stride, you extract a feature map. The next feature map, you're again doing convolution with padding and striding. That you can choose a different stride. But within an image, from one patch to the other, like for example, the first quarter of the image, I'm using stride 1. Next half, I would like to use stride 2. That is not typically done. Again, like although in theory, you could do that, but in practice, you would like that line that you would implement to have simpler arguments, right? For that reason, most of the pack, again, there's no need to reinvent a wheel, right? So you would not want to write that line of code from scratch. Somebody has written it, tried and tested. You would like to give some input number and padding yes or no type of argument, right? So that is what is typically used. So now in whatever we saw was for 1D illustration, but now you see that, okay, this is the animation. What would change? Again, the hop would change. You have some equation that tells what is the size of the image, right? So that size of the feature map at the output of the out after you use a certain stride, right? So again, like to just put this idea across, I give the equation, but what you see is that With padding, the size of the feature map increases, but with striding, the size of the feature map decreases, right? That's again common sense, but that puts put an equation. So when you are hopping larger, right? So you're moving faster, so the feature map size decreases. If I'm moving very slow, I'm gathering more features, okay? So from one feature map to the other feature map, it is one CNN layer. The input to a CNN layer is a feature map, output is a feature map. The first layer, the input is an image, the output is a feature map. If I put these, if I compose many such things, the input and output to a CNN layer is a feature map, okay? Yeah, so we will see all that, Pankaj. When do we need to reduce the size of the feature map and so on, right? What are the tools available? Okay, that is what will come next. So we have done padding, striding, convolution. Now, let's take a step back and see what are the things that we can play around with. Size of the filter. Do I need padding or no? Do I need striding? How large should be the stride? How many such convolutions do I need to put together? Do I need to choose different padding for every layer? Okay, and like what Pankaj was asking, like, okay, if there is some redundant information, can I subsample? So basically, these are the questions that people have asked and formally put together. Now, putting this together in different mix and match uh, uh, patterns give to different architectures that are out there. Okay, and the reason for this, many architectures will also I'll mention, but maybe we'll not have time to go through that today, but maybe in the beginning of the next lecture. Okay, so as I was telling, this padding and striding, you don't want to give numbers for padding at least, but you want to give an yes or no type of an argument. Okay, so that yes or no type of an argument is not yes or no, in fact, but it is same or valid. And valid padding is same as no padding. This is how Keras implements, right? So now some other PyTorch might have something else, or some other particular proprietary package might use something else, but this is more or less common. So whenever you use padding as valid, it is without padding. That means that these two layers, these two pixels are ignored. So here it is like an illustration with a certain filter size. So input is, I guess, 13, filter is, as we can see, it is 6, and you are using a stride of 5. That means you are skipping 5 to go to the next one, right? So this is first feature map, and this is the second feature map. If I do this, the next stride would be like after 5 at this point, right? So somewhere here, but this is not a valid operation because I don't know what to do, right? So what that means is I'm ignoring these two. I can only do 2 strides. So that is going to give me a size of 2 feature maps. The same padding, if I use same padding as an argument, what this basically does is this is going to pad zeros in such a way that if I use a stride of 1, okay, the size of the input and the output should be the same. That is why the name same comes in. But for all intents and purposes, what you need to keep in mind is if I use same, then there is some zero padding going on, and it is going to pad zeros as evenly as possible, might be uneven, but it is going to put some zeros on the left and right, top and bottom, such that whenever I use a stride of 1, the goal is that if the input is size 13, the output should be size 13. Now, if a different stride, then the size of the output obviously changes. So whenever you have to build a convolution layer, all you need to keep in mind is that dense that we had in Keras dense changes. I use a conv 2D, it could be 1D. we will ignore this for half a minute. We'll come back to this. I already hinted that one feature might not suffice. You need multiple features. That is this 32 number. I use 32 filters, each of size 3 by 3. I don't have to again say give 3 times 3. It is all uniform filters, right? So 3 size 3 times 3. Stride, it can be 1, it can be 2, and so on. Padding, same or valid. Either I give a ReLU activation function or a sigmoid activation function or something else, right? So these are the arguments that we can give in a convolution layer. If you're using a 1D convolution, the same story, right? I hope now this particular layer is clear. Now, in practice, what happens? We already asked these questions before. In practice, I'll not have an image that is one channel. I'll have RGB. Now, if I have multiple channels, what do I need to use? What is the math behind if I have multiple features? We will see all that. And also we will see some of the things like what happens if the feature is looking alike. Is there a way to do something, subsampling and so on? We will see that as we progress. Okay. So any quick questions at this point about padding, striding, convolutions, coding this single one layer of convolutions?
Professor, about padding, it's going to be, symmetrical, or it will be the same around width and the height. But when it comes to stride, it can be different. I mean, as we had seen in the previous example, it's 3 along height and 2 along width.
So see, padding, okay. Padding need not be symmetric, right? So all you get to choose is an argument which is same or valid. Valid means no padding at all, that's clear. Same padding, it is kind of automatically deciding how many zeros to add, how to add. So the logic is like it is going to add as evenly as possible, but in this illustration, it need not be symmetric as we see. The logic is if the stride is 1, it is going to add as many zeros evenly to match the input and the output size. Now, although in theory it is possible to choose different strides horizontally and vertically, you see that the only argument that you get to give is a number, which means that both horizontally and vertically you're using the same stride. And this particular illustration, just for the math, this is like, okay, I mean, if you don't want to use for some reason you don't like Keras, PyTorch, anything, you say I would like to code it everything from scratch, then you have that flexibility.
When we say strides equal to 1, that means
so you do, so after this you do this, right? And the next one is this, right? So you just hop 1 pixel.
Okay.
Right? Stride is basically like the walk length.
And when padding equal to same, that means when we say strides equal to 1, then output sizes, input size, meaning the features don't reduce at all. I mean, if it's an intermediate layer.
Yeah. So when we use same padding and stride is equal to 1, the way Keras pads 0 is to ensure that the size of the input and the output will remain the same. So what that means is, like, if we go back and look at this equation, so suppose I use here, right? So you basically say stride is 1, right? So this is 1, this is 1, this is 1, this is 1. Now filter is kind of fixed, in this case 2, and then the image size is kind of fixed, this is 3. Now this is whatever comes out is the size of the feature map. Now the unknown here is pH. So suppose this is 3 by 3 and this is 3 by 3. Now you figure out what should be P so that the input is same as the output.
Okay.
That is the underlying computation that line would do when we call same. I mean, yeah. So when we call same, yeah.
That means the feature map does not change at all, or it is okay.
So the entry of the feature map changes, but
Yeah.
the size of the feature map remains the same.
Okay.
And
It
often, yeah.
Meaning it could input and output feature maps could be different, but the size would change. Sorry, size would remain same.
Size should remain same. The entry should change.
Okay.
If we choose stride is equal to 1, if stride is not equal to 1, then it's based on the formula.
Okay.
Yeah. So,
Thank you.
Tripti?
Yeah, so Professor, you already explained in between the correlation between stride and padding, right? So when the padding is same, we can have, I mean, what is the optimum values can we give into the stride? Strides equal to 1 means whatever we provide as input, the output will be same.
No,
If we
the output size would be the same.
size
So,
would be same,
yeah,
right?
the entry of the feature would be different. We will see what are the typical numbers that are used in most of the common architectures. I will also tell why, what to use when. Okay. So these numbers, the choice of these numbers, this is just to get the concepts in place. But in practice, yeah, you might not choose 32 filter size, you might choose something else. But the general prescription I'll give maybe, if not today, the beginning of next lecture.
Thank you, Professor.
So Gaurav, to answer in short, what that means is stride has a consequence on the memory, right? So for example, like yeah, like what we were discussing, if I choose padding is equal to same and stride is equal to 1, then I might be extracting features, but eventually after 10 layers, I'm still storing maybe 10 times as many images and maybe 32 times 10 as many images that I started with, right? So there is also some trade-off in terms of how much I can overload and consume memory. So although it is desirable that, okay, I might want to use larger feature sizes throughout, but my memory limitation helps me, forces me to choose the filter. So as I said, again, recall, what is emerging out of all this discussion is that padding and striding are two knobs. One is telling, okay, if I use a very small stride, the size of the feature map increases, right? Or remains the same. Doesn't increase, it remains the same. But padding, the rate at which it decreases changes. So I can basically use a larger stride to basically shrink the size of the feature map. Padding, I can basically use those two to control these edge effects and so on, right? So that is the two handles.
Thanks, Professor.
This particular computation is simply coming from this formula that we see here, right? So nothing different. So you just plug in these numbers, you would get those parameters.
So, Professor, just one thing. So
what I'll do is, Gaurav, I'll launch this poll and then I'll take your question. Okay, in the interest of time. Yeah, so this is about padding and striding. Basically, the just for you to pause for a minute and then reflect. Yes, Gaurav, go ahead.
So generally the strides that we keep, I mean the number for the stride and the padding, so it's usually higher than the padding. Is that right? Is that the correct understanding?
So padding, as I said, like most of the functions that you would use, you will not get to key in a number. So you would just say, I want a padding or I don't want a padding. That is what you would give. And the pads that typically you're right. Stride is upper bounded by the number of pixels. but padding, there's no upper bound on that.
Okay.
Right. So that is what is the limiting case. Okay. So I would end this poll now. Okay. So as it's clear, the padding can increase the height and the width of the output. It's not allowing you to shrink the size of the pixels, but strides can reduce the resolution of the output. So again, like imagine the beach example case. I'm moving very fast. So that basically means that I don't want my feature map to have a very high resolution. I can do a scan very fast, which also means that the resolution of the feature decreases, right? So, and in terms of the memory also, that gives me a smaller feature map.
Professor, just here, if I can ask, this resolution reduction is also equal to like reduction in height and width. Can we say like increasing height and width for padding is increasing resolution? Can we say that way? Or
Padding is not giving any additional memory, I mean, additional information to the image, right? It's basically zeros. Whatever image was there, it's only increasing in the size, but it's not making any image, it's not making an image sharper, for
so
instance.
resolution may be giving some information or reducing or giving.
Yeah. So, so imagine that I have a feature map which is kind of repetitive. So that is kind of like, okay, if I zoom in also, just like what we mean by resolution, right? So look at like a 1 megapixel image and a 30 megapixel image. The image,
there
the
won't be
information
much
conveyed
information.
is same, but if I now zoom in, that quality is preserved.
Understood.
Okay, so now how do we put this in practice? And there is one more particular feature related to already what I mentioned. So what I'll do is I'll quickly go through that and maybe flash the architecture, and then we will come back to this a bit more in detail in the interest of time, right? So maybe 5 to 10 more minutes, bear with me, and then we can put all these together in place and then revisit this in the next lecture. So what we already saw was the following, right? So we saw that the images are not single channel. And what I already mentioned is that oftentimes features we require to extract multiple features, not just one feature. So that is what happens in practice. Now to do this, what we need is a following. I require many filters. So if I require, say, 10 feature maps at the first convolution layer, I require 10 filters. And each could be of size, say, 3 by 3. Okay, that was the first argument. So if I use 10 filters, I'm going to get 10 feature maps. So each slice here is a feature map. Okay, so I get a stack of these feature maps. Now, the input stack typically is an RGB. This RGB might become something else, right? So it can become something else as we progress. For example, I'm using a vertical, horizontal. Hopefully that is what is going to learn. And I'm going to do this. So now what you see is on the right is an animation of how the computations are progressing. Maybe what I'll do is I'll pause that animation and then if I do this, I don't know if it continues. No, it will not. Yeah, so let's take a look at this. Now, what is going on is, say, I have RGB, 3 channels at the input. Now, what we require at the output is 2 feature maps. Feature map 1 and feature map 2. Now, what you need to take home as a message from this picture is the following. So I have 3 input features, feature maps. I want 2 output feature maps. Now, the question is, how many filters in total we need? Okay. And that basically determines how many parameters that we are training. Now, what we see is that clearly the number of parameters that we require depends on the number of feature maps we desire and the number of input feature maps. So we have 2 filters, W0 and W1. W0 is for the first feature map output. W1 is for the second output feature map. And what is also important is for each of this output filters, W0, W1, I have as many as filters as the number of input features. So I have 3, right? So 1, 2, and 3. This corresponds to R, G, and B. This is for the output 1. This is for output 1. This is for output 1. Okay. So now repeat the same. Output 2, output 2, output 2, R, G, and B. So the number of parameters depends on the number of input layers and the number of output layers. Now, what is going on is the following. You do a pointwise multiplication and addition as before. Then at the end, to get to this feature map, you simply add all those. Okay. That is this equation that we see here. The PDF will have a static view. I'll see how to get this animations, but yeah, this PDF itself is like a very large size, but yeah, we'll see how to do that. But typically we send a PDF. So now when we have multiple features, this is what we require. What you need to keep in mind is the weights and biases. For the sake of understanding, you see some numbers, but these are learned via stochastic gradient descent. Okay. So again, what is desirable is many output feature maps. One feature map cannot capture everything going on, which also means that more feature maps I require, I need to learn more filters, number of parameters increases, and that is determined by the number of input features, number of output features, and the size of the filter, right? So now in this particular case, you just need to add all these numbers, 3 times 3 times 3, I think 27, 27 times 2 plus 2 for the bias, right? So that is what you require. So 27 plus times 2 plus 2, right? So these are the total number of parameters for this particular cartoon illustration is what we require. Now, this is an illustration of training on a particular set of data sets, which is called as an ImageNet data set, and training for that particular challenge and seeing what are the filters that look at the initial layers. So the first layer of the convolution. Now, if you look, what we had in mind is that the initial layers should basically extract all these basic features, right? The color maps, horizontal, vertical lines, and so on. And in fact, the convolution neural network is actually doing that, right? So this is basically a dump of all these 3x3 filters that was obtained after training a neural network. And what we see is that it is extracting all those basic features that would be required to synthesize an image, right? So that is quite remarkable. And while we designed this neural network, we wanted it to do so, right? But there is no way forcing it to do so, right? But Now, when you put these things properly in place, when we converted whatever we discussed in English while describing how to find Waldo, when we put together systematically in a principled way uh, as a computer program with respect to the underlying math, we see that it is actually behaving how we would actually work with images. And that is one of the reasons why you see great success with all the image analytic tasks that you would see, right? So either it could be simply, programming a robot for perception or object detection, etc. Right? So this can be put in place for many tasks that we can envision.
Sir, I have a question here. While this feature mapping, when we are considering RGB 3D features, right, three-dimensional, so during this process, internally, are we converting, are we flattening it? Like while the feature map happens, we are not considering as 3D, rather as 1D. Or
No. So throughout this imaging, you're never using flattening.
okay.
So that was the whole. So we would like to process this 2D image as a 2D image itself. So you would use 2D convolutions to go pixel by pixel, right? So you are not flattening it.
Okay.
Right. So when you flatten, oftentimes you also lose the structure in the image, right? So for example, like, okay, the image of this boy was something like this, right? Now, if I stack column wise, then the structure in the image would go, right? So this guy would come somewhere here and so on. That structure is gone.
Right.
So we would not, whenever we are doing conv 2D, we are using image as is. We are processing image by looking at one patch at a time. Okay. And the input layer, the way you should see that is input layer is also a feature map. Except that the input feature is 3, right? So there are 3 feature maps. Right. So what is going on from here to here is also a convolution layer. So there are 10 feature maps that becomes, say, 6. Right. So 10 to 6, some example number. So 3 to 10, except that happens to be the input. That is all you need to keep in mind. So whenever you look at an image, the input is actually like, say if it's a 12 megapixel or like, 100 by 100 image. So you would get it as a tensor, right? So whenever you look at a raw file of an image, you already have these 3 RGB channels.
Correct.
So that's the default image.
Okay. Thank you, sir.
Okay. So pooling, I would skip this for now in the interest of time. We'll come back to this in the next lecture. But the basic idea with pooling is it's a box with no learnable parameters, and it is basically going to subsample the image. So if you look at what this image is, this was the architecture that we used many slides back. If you look at this image to this image, whatever information is being conveyed from this larger image is also being conveyed in the smaller image. Except that what I do is with pooling, there's no training going on. It is basically subsampling. I represent all these pictures in one patch with one pixel, right? So that's called as a max pooling. So I replace this with max intensity or average intensity. I would get a reduced sized feature map. Why would you use that? Suppose if you have an image or a feature map that has too much of redundant information, then you can reduce the size of that feature map without much loss of information, right? So there is loss of information, but without much loss of information. And that is useful in reducing the memory and the computational usage. Okay, so that is one more box, right? So max pooling operation, you would basically use this particular layer and you would say like, okay, give a pool size, which is basically the size of that pooling operation. You look at 2 by 2 pixel, replace it with 1 pixel value. Okay. So I think now we are in a good place to put these things together to give the CNN architecture. Okay, so this is the last slide I will use now, and we will come back with a bit more discussion in the next lecture. So now recall, what did we do? We did a lot of things. Pooling is kind of a compression operation, right? So depending, it's like not fancy compression like JPEG or anything. It's basically a very stupid way of subsampling, right? I take a look at 2x2 pixel or a 4x4 pixel, depending on what size we give, and you replace that with one particular value, either an average or a max or a min, right? So you take some numbers, replace it with one number. Okay, that's the stupid compression that we are doing. Okay, why do we do that? It could be that the features that I'm getting is of very high resolution for whatever reason, choices of the padding and the striding I'm using, but I would like to now compress it to deal with the memory constraint I have. Okay, so now recall, what did I say in the first class? I mean, the beginning of today's class, that we have some basic building blocks to put together a CNN architecture. These are useful for extracting features. Now, in this particular illustration, what we need is to decide what type of a vehicle it is. Now, if there is a feature engineer, a domain expert with you, what is he going to do? He's going to give you features like the physical dimensions, engine capacity, mileage, list of features that are relevant for this particular example, and then put it as a table. He is a feature engineer for you. Okay, now you're going to pass it through your favorite softmax regression or MLP classifier to give a class output, whether it's a car, truck, van, or a bicycle. Okay. Now, I don't have that domain expertise with me. I don't have this automobile engineer with me. I don't have common sense to decide whether what is a car or what is a truck. Then what do? I throw this to a convolutional neural network, which is going to just look at the raw image. I have that much sense to take pictures, put it to a computer. Now, what are you doing? You're running a set of convolution operations, convolution layers, extracting many features. What we have seen is that for that image and example, you have interpretable features in the beginning, which means that if you take a look at those features, the filters, it's going to learn something meaningful. As you go deeper and deeper, it becomes more abstract. Abstract as we go ahead. So you use convolution pooling. This is a typical architecture. You might skip a pooling operation, but you require two convolutions, one pooling. All those mix and matches you could play around with. Now, you have extracted all the features that are required after many convolution layers. Now you need to make a decision. Here you use an MLP classifier. You train everything in an end-to-end fashion to get the final softmax scores. For this example, if you want to put a bounding box, you use a regression. Okay. So any major convolutional neural network architecture, you see, it comprises of these building blocks. You play around with the number of convolution layers, filters, etc. You get different architectures. If you want to model this in Keras, you have a convolution layer, a max pooling layer, a conv layer, max pooling, and so on, right? So keep on doing this. At this point, you still have a feature map. You would flatten it, make a vector that is for the decision layer. Okay. So now here is what we already saw in the last lecture and beginning of today's lecture. It's an MLP classifier. At the end, you have a softmax. Remaining all the story that we discussed about how to choose the number of neurons, how many filters, etc. We will see in the next lecture, right? So it will also give us a chance to revisit this after you play around with this particular model in the sessions during the week, right? So play around, program this. But the basic idea is now a convolution layer has number of filters, filter size, activation, whether I need padding or not. Okay. So that basically is a CNN architecture. Now we will, what we will do in the next lecture is see some applications of this, see different architectures like AlexNet and so on, and also go through a bit more in details when to choose, how to choose the number of filters, all these details. And also I will come back to that, one of the two things that I wanted to cover with MLP in the next lecture. So that's more or less what I had to cover today. I hope it was informative, and I'll be happy to take any questions that are left over now, or in case I did not answer any questions now, you can feel free to unmute yourself and go ahead. So you get a basic essence of what CNN is, play around with during the week, and then we will come back so that you have now some more questions or a better feel of what is going on. MLP part, I can do it now. If I see many thumbs ups, I'm okay with that, right? So I'm okay to go for 10 more minutes, but I don't want to overload you guys more than what is needed. It's okay that we do it beginning of next lecture, right? So it should not basically, it is kind of a modular thing, so it is fine. All of us are also hungry and maybe like too much information. Maybe a fresh look, right? So I would consider that we do it. I don't know what S means, but is cover now or next week, right? So it will be like, yeah, I mean, let's not overload ourselves. It's okay. Yeah. So it's a modular thing. You would not lose much, but I promise to cover it in the beginning of the next lecture.
Professor, I have a question. When we apply a certain padding at the input layer, does the same? I mean, it's going to be only for the image, or
No.
even?
Yeah. So what? So as I mentioned, you should not differentiate between the image and the feature map.
Yeah.
So in input is feature map 0. And you could do padding to that. The feature map 1, you could do padding as well.
Okay.
Right? And padding as such is not changing the information content in the image. It is basically putting zeros. It looks a bit ugly, right? So I put a lot of white patches around this building. It looks ugly, but as that building, or the building will not become something else, or the car will not become a truck.
Yeah.
Right? So that is the main thing, but you would also want to capture whatever is there in these edges so that it's a valid operation for convolutions that we have, right? So that's the reason.
And if the image is mostly centered and doesn't have much information in the boundaries, we don't use padding. Is that how it is, or?
Yeah. So yeah, if you're looking mostly like these MNIST type of images, then padding might not really help much, except for the fact that in case you require to go a few more layers deeper, then you might require a few padding layers, but otherwise, as such, it's not going to change much for the boundary effects.
Okay.
And yeah, so these are actually the things that you can try out, right? So for example, this MNIST, fashion MNIST, instead of, the first part of the exercise, you could do MLP classifier. The next part, you could replace dense with conv, and then, padding with valid, same, right? So we could try this out ourselves and see that nothing much changes. But as I said, like using MLP classifier for this MNIST, fashion MNIST is already an overkill. Now, using CNN is also much more of an overkill, but for better understanding, this is nicer examples rather than looking at like 100 CFAR images, etc., right? With 100 classes and so on. This is like much more intuitive to understand.
Okay. Professor, one more question. When we use parameter sharing, that is mostly when the information is related and ordered. In case of images, when it's 2D, and in case of speech, it's 1D. Is it that when a person is delivering a certain speech, then there won't be a lot of changes?
Correct. Yeah, I mean, see, whenever you're speaking, I'm speaking.
Yeah.
If you look at, there is a certain pattern to that, right?
Yes.
Otherwise, it will sound like noise.
Yes.
And that's not necessarily with speech alone. Most of the time series data 1D
Yeah.
have that pattern. Although, we will see that when we are discussing the sequence model for time series, we would use something known as a recurrent, or video processing or time series. We would use something known as a recurrent architectures, where the initial layers could be CNNs, which would extract features over a certain window.
Yeah.
And they're using CNNs to do complete time series processing have also some limitations like what we discussed today with respect to memory explosion, right? So with MLP for using 12 megapixel, we'll see what it means to use MLP or CNN for time series that is of infinite length. So
Yeah.
we can use CNNs to extract features initially.
Okay. And parameter sharing is specifically because they are ordered or related.
So with respect to parameter sharing, so as we saw, like for every patch that we visit,
Yeah.
we are using the same set of filters.
Yes. Yes.
So
Yeah.
what that means is, like, over this image, I'm using the same set of parameters,
Yeah.
right? So now if I put this as a big W matrix and a linear operation, that W will have like repeated entries. So that is where the parameters are being shared.
Yeah. Okay. And it's due to the data being related to each other, as in pixels.
Correct. Yeah.
In such a case, when it comes to audio, a speech would be different from musical content. Musical content would be unpredictable. I mean, in that case, will it work, or will parameter?
We will see. I mean,
Okay.
some of the architectures, like in the next class, not leave.
Okay.
Let the surprise be as it is. We'll
Sure.
see what it happens for music as well.
Okay. Yeah. Thank you, boss.
Rupesh?
Yeah, Professor, my question is like if there are multiple filters present in a layer, so the output of that particular layer will be those many number of feature maps, is it?
Yes. So if I require like say 10 output feature maps, I require 10 filters.
Okay, the same you have reflected in the image net where for a given in this.
Yeah, here, right? So here,
Yeah,
like I require two, going from 3 to 2. So I require two. W0 is for output feature map 1, W1 is for output feature map 2. But each of these filters are 3 by 3 times 3.
Okay.
3 is corresponding to the
For
inputs.
the channels, yeah.
Yeah. Okay.
Okay. And these weights are being learned by backpropagation, which is not built
Correct.
yet.
Yeah,
Right?
so nothing changes, right? So whatever we discussed, like the mini batching, epoch, the optimizer choice, etc. Right? So only thing that is changing now is I'm replacing this dense layer with a conf and a max pooling layers. Right? So once you have this model, you'd still use compile model with optimizer being SGD and loss being MSC or softmax, I mean cross entropy and so on. So only this part changes, the remaining part related to compile, etc., that remains the same.
So what I understand is if we increase the number of filters, the size will be increasing, like the data to store, but it may not be increasing at that rate of the input image megapixel size.
Correct. Yeah.
So
That's
that is
right.
how we are saving.
Yeah, that is how you're saving, and more, even more so, you are having a controllable growth in the number of parameters. And the number of parameters we can easily compute using that model summary, right? Whatever I mentioned. But Now I can use the same architecture to process a 12 megapixel image or a 28 by 28 megapixel image, right? So in other words, the number of parameters is not depending on the size of the image.
Size of the image.
Yeah, that is the main advantage. Okay. Okay, I see that I've answered most of the questions. In case I left out, you can unmute and ask. Otherwise, we can pause today's lecture here and resume back next Saturday. Okay, so I don't see any further questions. So thank you all. So I'll make this PDF available and we'll see how to make the animations available. But I guess the animations will always be through video that you can always see. So thank you all, and I'll see you next Saturday. Take care till then.